There is a moment before the first star, before the first atom, before the first second, where everything we will ever know or love or discover simply did not exist in any form we would recognize. Not darkness, because darkness requires space to be dark inside. Not silence, because silence requires time to pass in. Just an absence so complete that even the word absence fails to capture it. And then, from that incomprehensible edge of non-existence, the universe arrived. Space began stretching, energy flooded everything, the rules of reality switched on one by one, and somewhere in that opening act, the conditions for chemistry, for biology, for consciousness, for curiosity itself, were quietly written into the fabric of what became the cosmos. We spend our entire lives inside this universe, surrounded by its stars and galaxies, breathing its atoms, running on the energy of a star it produced, and yet we have the audacity to ask how it got here. Not just how it evolved once it existed, but why it exists at all, what put it here, what the moment of its arrival actually was, and whether the word moment even applies to something that may have also created time itself. This is not a comfortable question. It does not have a tidy answer waiting in a textbook somewhere, wrapped up and filed under solved. It lives at the very edge of what human knowledge has been able to reach, at the place where our equations become strange, where our language starts breaking apart under the weight of what it's trying to describe, and where the most honest answer a physicist can give is that we are still working on it, and the working is itself magnificent. What we do have is evidence. Extraordinary, hard-won, repeatedly tested evidence that tells us what the universe was doing in its earliest measurable moments. Evidence that the universe began in a state of tremendous heat and density. Evidence that it has been expanding ever since, that the expansion stretched the light of ancient events into long red wavelengths we can measure today, that the cooling left a faint afterglow of radiation still filling all of space in every direction. Evidence from the chemistry of stars and ancient gas clouds that the first minutes of cosmic history ran like a nuclear furnace and left behind a specific set of light elements in predictable proportions. Evidence from the pattern of galaxies across the sky that the universe has been building structure through gravity for billions of years, assembling small fluctuations into the vast web of clusters and filaments we now inhabit. The Big Bang model is not a guess. It is not a creation myth dressed in equations. It is a framework that has survived decades of increasingly precise testing, and it keeps surviving because it keeps correctly predicting what we find when we look harder and deeper. But here is the thing that makes it so philosophically electric. All of that evidence, all of that precision, all of that successful prediction describes what the universe was doing. It does not, on its own, tell us what caused it to begin doing those things. It does not tell us what existed before. It does not even guarantee that the word before is meaningful in this context. That is the gap we are going to explore. Not with speculation dressed as certainty, not with a single satisfying narrative handed down as though the question is closed, but with the actual tools of physics and cosmology, wielded carefully, with their assumptions named and their limits acknowledged. We are going to follow the evidence as far as it goes, and then we are going to be honest about where it stops and what lies beyond the edge. Because the most scientifically honest and most philosophically stunning thing about this question is that even the shape of the question might be wrong. The demand for a cause, the insistence that something must have triggered the beginning, the intuition that nothing cannot produce something, all of these might be the wrong conceptual tools for a domain where time itself is part of what needs explaining. When you ask what came before the Big Bang, you may be doing something like asking what is south of the South Pole. The question sounds legitimate. It uses real words. It follows real grammatical rules. And yet it may simply not correspond to anything real, not because the universe is hiding something, but because the concept being applied does not extend into the domain being asked about. We will look at why physicists think that, and we will look at the alternatives, the models that try to give the beginning a cause anyway, that replace the singular starting point with a transition from something earlier, or that locate the universe's origin in a quantum process that dissolves the need for a prior moment. Each of these ideas carries its own assumptions, its own predictions, its own costs, and its own areas where the data is not yet sharp enough to decide. This is what responsible exploration of origins looks like. Not comfortable certainty, but disciplined inquiry at the edge of knowledge, where every answer opens 3 new questions, and where the size of what we do not know is itself a measurement of how far we have come. We begin where all good investigations begin. What we can actually measure. The universe is telling us its history all the time. Every photon that enters our instruments, every spectral line we analyze, every subtle statistical pattern in the distribution of galaxies carries information about the past. The universe does not narrate, it does not explain itself, it simply leaves traces, and we have spent the better part of a century learning to read them. The first and most fundamental trace is that the universe is expanding. Not in the intuitive sense of stuff flying outward through pre-existing empty space, the way shrapnel flies from an explosion, but in the deeper sense that space itself is growing, that the distances between things are increasing because the metric of spacetime, the underlying ruler against which all distances are measured, is changing. That distinction matters enormously, and it matters especially for what we are trying to understand about origins. If you imagine galaxies as dots painted on the surface of a balloon, and you inflate the balloon, no single dot is at the center of the expansion. Every dot moves away from every other dot. From the perspective of any dot, all the others are receding, and the ones farther away are receding faster. That is not because distant galaxies are moving faster through space in the local sense, but because there is more expanding space between us and them, so the accumulated growth rate of those distances is larger. The expansion is not happening in some location. It is happening everywhere, including in the space between you and the screen you are reading this on, though the effect on human scales is incomprehensibly small. We detect this expansion through redshift. Light from distant galaxies arrives stretched toward longer, redder wavelengths than it had when it was emitted, because the space it traveled through grew during its journey. The wavelength grew with the space. This is not the same as the Doppler shift you get from a passing ambulance, though the math looks similar at low speeds. At cosmological distances, it is a purely geometric effect. The photon's wavelength is stamped by the universe's scale factor at 2 moments, emission and arrival, and the ratio of those scale factors is printed into the photon's wavelength as a number we can measure. When we plot how fast galaxies appear to be receding against how far away they are, we get a relationship called the Hubble law, named after Edwin Hubble, who helped establish it observationally in the late 1920s, though many others contributed to both the observations and the theoretical framework that preceded them. The relationship is remarkably clean given the messiness of galaxy distances. Recession speed scales with distance. Double the distance, roughly double the recession speed. The proportionality constant, the Hubble constant h0, tells us the current rate of cosmic expansion, and it has been one of the most fought-over numbers in modern cosmology because different methods of measuring it give slightly different answers, a tension that may be pointing to missing physics in our models. Measuring distances in astronomy is not straightforward. You cannot use a tape measure. You cannot even use parallax, which is the geometric method of inferring distance from apparent position shift against background stars beyond a certain range. So astronomers build what they call a cosmic distance ladder, a sequence of overlapping methods each calibrated against the previous one, each extending the reach of the previous one, each carrying its own sources of uncertainty. The bottom rung is geometric parallax, extended enormously by the Gaia space mission, which has measured positions and motions of over 1 billion stars with exquisite precision. Above that are pulsating stars called Cepheid variables, which obey a well-established relationship between their pulsation period and their intrinsic luminosity. If you know how bright something truly is, and you measure how bright it appears, the ratio gives you the distance. Cepheids are bright enough to be seen in nearby galaxies, and they anchor the next rung. That next rung is the type Ia supernova, which are stellar explosions that reach such extreme brightness they can be seen across billions of light years. They are not perfectly standard candles, but their peak brightness correlates with how quickly they fade, and that correlation, once calibrated with Cepheids in the same galaxies, makes them the most powerful distance indicators we have across the deep universe. Using type Ia supernovae, astronomers in the late 1990s discovered something that shook the field. They expected the expansion to be slowing down under gravity. Instead, distant supernovae were dimmer than expected, meaning farther away than expected, meaning the universe was not decelerating but accelerating. The expansion rate is increasing. Something is driving the universe apart faster and faster, and whatever that something is, it has been named dark energy, and it accounts for roughly 70% of the universe's total energy budget today. We can measure its effects with extraordinary precision, but we cannot yet explain what it fundamentally is, and that ignorance sits at the heart of modern cosmology like a splinter we cannot quite reach. This accelerating expansion is not the primordial Big Bang expansion, but a late-time takeover. In the early universe, matter and radiation dominated and slowed the expansion. As the universe grew larger and matter diluted, dark energy, which does not dilute with expansion, eventually took over and began driving acceleration. We are currently living in the era of dark energy dominance, which is either a cosmic coincidence or another clue pointing to physics we do not yet fully understand. But expansion, even well-measured expansion, only tells us the universe has been growing. It does not on its own prove it began hot and dense. You could imagine an expansion that started from some cold, thin state and remained cold and thin forever. What locks in the hot, dense early phase is the second great pillar of evidence. In 1965, Arno Penzias and Robert Wilson, working at Bell Laboratories in New Jersey, were trying to trace a persistent microwave hiss that contaminated their horn antenna. They checked for instrument malfunction. They drove to the antenna and removed pigeons that had nested inside it, cleaned out the mess the pigeons had left, and checked again. The hiss remained, at the same level in every direction they pointed the antenna, stable across seasons, completely independent of any terrestrial source. It was coming from the sky, uniformly, from everywhere at once. What they had stumbled onto was the cosmic microwave background, the relic radiation left over from the early universe's hot, dense phase. When the universe was young and hot, it was filled with a plasma of protons, electrons, and photons all interacting constantly. Photons could not travel far before being scattered by free electrons. The universe was opaque. But as it expanded and cooled, the temperature eventually dropped to the point where electrons could bind to protons to form neutral hydrogen atoms. This happened around 380,000 years after the hot phase began, at a temperature of roughly 3,000 Kelvin. When neutral atoms formed, the free electrons that had been scattering photons disappeared from the plasma. Suddenly, photons could travel freely. The universe became transparent. And those photons, released at that moment of transparency, have been traveling ever since, cooling as the universe expanded, stretched from visible red light into infrared and eventually into microwaves. Today, they fill all of space with a temperature of about 725 Kelvin, just barely above absolute zero. That temperature, and crucially the shape of the radiation spectrum, is definitive. The CMB has a nearly perfect blackbody spectrum, which is the signature of thermal radiation from a system in equilibrium. A blackbody spectrum does not arise from any random process. It requires genuine thermalization, a state of genuine heat and density in which matter and radiation mixed and exchanged energy for long enough to reach equilibrium. There is essentially no alternative explanation for a blackbody spectrum filling all of space in every direction. The early universe was hot and dense and in thermal equilibrium, and the CMB is the fossil of that state. The precision with which the CMB matches a perfect blackbody is itself remarkable. The COBE satellite measured the spectrum in the early 1990s and found it matched the theoretical curve to better than 1 part in 10,000. This is one of the most precise agreements between theory and observation in all of science. The universe was not merely warm, it was in genuine thermal equilibrium, and that state has left an essentially indestructible record in the radiation that fills all of space. But the CMB is not perfectly uniform. That is the third crucial detail, and it is where the CMB goes from being evidence of a hot past to being a detailed map of the early universe's structure. The temperature varies across the sky at the level of about 1 part in 100,000. These tiny variations, detected definitively by the COBE satellite and mapped in increasing detail by WMAP and Planck, are not noise. They are signal, and they carry an enormous amount of physical information. The variations arise from acoustic oscillations in the early plasma. Before recombination, the universe was a fluid of photons and baryons coupled together, resisting gravity's tendency to clump and oscillating instead like sound waves in a medium. Where matter was slightly denser, gravity pulled it together, but radiation pressure pushed back. The overdense regions compressed, heated, pushed back, rarefied, cooled, fell back together, and oscillated in a rhythm set by the speed of sound in the plasma. When recombination happened and the plasma froze, these oscillations were caught mid-cycle. Regions that happen to be at maximum compression at that moment are slightly hotter in the CMB. Regions at maximum rarefaction are slightly cooler. The pattern of oscillations frozen into the CMB sky is what produces the acoustic peaks in the power spectrum, the characteristic sequence of hot and cold spots at preferred angular scales. These peaks are extraordinarily informative. Their positions and heights depend on the composition of the universe, how much ordinary matter is present, how much dark matter, what the geometry of space is, what the expansion rate was at recombination. By fitting the observed power spectrum to theoretical predictions, cosmologists can extract these parameters with remarkable precision. The CMB is, in effect, a precision measurement of the universe's ingredients. One of the most striking results of CMB analysis is that the universe appears to be spatially flat or very close to it. This means the geometry of large-scale space follows Euclidean rules. Parallel lines remain parallel. The angles of a triangle add up to 180 degrees, and the expansion rate has a specific value that places the universe right at the critical density that separates eventual collapse from eternal expansion. Flatness is not a trivial measurement. It constrains the universe's energy content and tells us that dark matter, dark energy, and ordinary matter together account for almost exactly the critical density. The CMB also reveals the seeds of all cosmic structure. The tiny temperature variations are the imprints of the density fluctuations that, amplified by gravity over billions of years, grew into the galaxies and galaxy clusters and cosmic filaments we see today. Every galaxy you have ever seen in an astronomical image, every cluster, every vast empty void in the cosmic web, traces its origin to a tiny fluctuation in density at the surface of last scattering. The CMB is not just a fossil record of the hot early universe. It is the blueprint from which the visible cosmos was built. The third major pillar of evidence comes from the chemical composition of the universe, specifically from the relative abundances of the lightest elements. Big Bang nucleosynthesis is the process by which protons and neutrons in the hot early universe assembled into light nuclei during the first few minutes of cosmic history. In the first seconds, the universe was hot enough that protons and neutrons were in equilibrium, converting back and forth through weak interactions. As the universe cooled and the weak interaction rate fell below the expansion rate, this equilibrium froze out, locking in a ratio of neutrons to protons determined by the temperature at that moment. From this point, the universe's nuclear fate was set. As temperature continued to drop, free neutrons could no longer convert to protons through weak interactions, but they could still decay with a half-life of about 10 minutes. The race between neutron decay and nuclear assembly became the defining competition of the next few minutes. As the temperature fell through the range suitable for nuclear fusion, protons and neutrons began assembling into helium nuclei. Deuterium was the bottleneck. It forms when a proton and neutron combine, but in the hot early universe, it was immediately photodissociated by energetic photons. Only when the temperature fell enough for deuterium to survive could the chain proceed to helium. This deuterium bottleneck delayed nucleosynthesis and gave more time for neutron decay, setting the final neutron-to-proton ratio that determined how much helium could form. The prediction is that roughly 25% of the baryonic mass would be in the form of helium-4, with the remainder mostly hydrogen, plus small amounts of deuterium, helium-3, and lithium-7. These predictions depend on one free parameter, the baryon density, meaning the density of ordinary protons and neutrons. If you know the baryon density, you can calculate all the primordial abundances. If you can measure even one of them precisely, you can infer the baryon density and predict all the others. Observations have borne this out with stunning precision for most elements. Deuterium is measured in ancient, pristine gas clouds seen in absorption against distant quasars, gas that has never been processed through stars and therefore preserves its primordial composition. The measured deuterium abundance matches the nucleosynthesis prediction and implies a baryon density that is in excellent agreement with what the CMB power spectrum independently requires. This agreement across completely different physical processes and measurement techniques, separated by hundreds of thousands of years of cosmic history, is one of the most powerful consistencies in all of science. Helium-4 is measured in metal-poor galaxies where stellar processing has been minimal, and the inferred primordial helium fraction is consistent with the prediction of roughly 25%. Lithium-7 is the troubled member of the family. Old, metal-poor stars contain less lithium than standard nucleosynthesis predicts, a discrepancy known as the lithium problem that has persisted for decades and has no universally agreed resolution. It may involve stellar physics that destroys lithium after the fact. It may hint at non-standard early universe processes. The discrepancy is real and acknowledged, and it illustrates that even a successful model leaves room for unresolved tensions. The convergence of these three pillars, expansion history, CMB temperature and anisotropy, and light element abundances, is what makes the hot Big Bang model so compelling. Each pillar involves different physical processes, measured with different instruments using different techniques, constrained by different theoretical calculations. They could easily have disagreed. The fact that they agree, that a single consistent picture of a hot, dense, expanding early universe explains all three simultaneously, is not a coincidence that can be hand-waved away. It is a quantitative triumph that has been tested and retested for decades. But this convergence also makes precise what the model is and is not claiming. The Big Bang model is a description of how the universe evolved from an early hot dense phase. It is not a description of what caused that phase to exist. It is not a description of what happened before that phase, or whether before is even meaningful. It is not a claim about the first instant of time, because the first instant may be outside the domain where the model's equations apply. The singularity that appears when you extrapolate general relativity backward, the mathematical point where densities and temperatures formally diverge to infinity, is not a description of a real physical state. It is a signal that general relativity is being pushed beyond its domain of validity. When any theory predicts infinity, it is usually telling you that some crucial physics has been omitted, not that infinity actually occurs in nature. In the case of the Big Bang singularity, the missing physics is almost certainly a quantum description of gravity. Classical general relativity treats spacetime as a smooth, continuous manifold that can be curved by matter. But at the densities and curvatures near the putative beginning, quantum effects on the geometry of spacetime itself must matter. And we do not yet have a complete, tested theory of quantum gravity that we can simply plug in. So the Big Bang, as a scientific model, earns its confidence through specific, measurable predictions that have been confirmed. But it points toward a boundary of knowledge rather than an ultimate explanation. The evidence carries us far, but not all the way, and the territory beyond the edge of the evidence is where the real philosophical and physical drama begins. What the measurements tell us is a story of exquisite consistency. But they also reveal ingredients whose nature we do not understand, and their presence shapes everything we can say about origins. Dark matter is one of them. The CMB anisotropy spectrum requires a component that does not couple to photons in the early plasma, that can begin clumping gravitationally before recombination without being held back by radiation pressure. This component makes up roughly 27% of the universe's energy budget. We infer its presence not from any direct detection but from its gravitational effects, and those effects appear in many independent contexts: galaxy rotation curves, gravitational lensing, galaxy cluster dynamics, the growth of large-scale structure, and the CMB itself. The case for dark matter from multiple independent angles is extremely strong. But its fundamental nature, what it actually is, what particle or field constitutes it, remains unknown. Every direct detection experiment has so far returned null results, and the absence of a detected particle has narrowed the field of candidates without identifying a winner. Dark energy is the other great mystery. Whatever is driving the accelerating expansion of the universe today, it constitutes roughly 68% of the total energy budget. The simplest description is the cosmological constant, a term Einstein originally introduced into his equations of general relativity and later described as his greatest blunder, though his reasons for calling it that involved a different application than the one cosmologists now use it for. A cosmological constant behaves like a uniform energy density filling all of space, with an associated negative pressure that drives accelerated expansion. It fits the observations well, but it poses a severe theoretical problem. Quantum field theory predicts that empty space should have a vacuum energy from the zero-point fluctuations of all quantum fields, and when you calculate this vacuum energy using the standard model, you get a number that is somewhere between 60 and 120 orders of magnitude larger than the observed dark energy density. This discrepancy, sometimes called the worst prediction in physics, suggests that something is almost perfectly canceling the quantum vacuum energy, leaving only the tiny observed remnant. We have no explanation for this near-perfect cancellation. Dark energy may not be a cosmological constant at all but some dynamical field that evolves over time, or it may point to a fundamental gap in our understanding of how quantum field theory and gravity interact. Both dark matter and dark energy are ingredients in the standard cosmological model, lambdictum, where lambda represents the cosmological constant and CDM stands for cold dark matter. This model fits an enormous range of observations with a small set of parameters. It is, by any reasonable measure, the most successful large-scale description of the universe we have, but it is a fitting framework rather than a fundamental explanation. It describes the ingredients and their behavior without explaining their origin or their nature. And its ingredients, comprising 95% of the universe's energy budget, are unknown to us at the level of fundamental physics. This matters for the question of origins because any story about what caused the Big Bang must also account for what put dark matter and dark energy into the universe, and in the right proportions. An origin story that explains the hot plasma but not these other components is incomplete. The parameters we measure with such precision are clues not just to what happened, but to what physics generated those conditions in the first place. The large-scale structure of the universe adds another layer of evidence and constraint. Galaxies are not randomly distributed. They cluster into groups, groups cluster into galaxy clusters, clusters string together into filaments, and between the filaments lie vast nearly empty voids. This pattern, the cosmic web, is visible across hundreds of millions of light-years and has been mapped in increasingly fine detail by surveys like the Sloan Digital Sky Survey and its successors. The statistical properties of this structure are predicted by the same primordial density fluctuations that appear in the CMB. A tiny overdensity of 1 part in 100,000 at the time of recombination, given enough time and the right matter content, grows through gravitational attraction into the galaxy clusters and filaments we observe today. Running the calculations forward requires knowing the initial fluctuation spectrum, the matter content, the dark energy content, and the expansion history, all of which are constrained by the CMB and supernova measurements. The predictions match the observed clustering statistics with remarkable accuracy, providing another consistency check on the standard model. One particular feature of the large-scale distribution deserves attention because it connects the CMB to galaxy surveys in an especially clear way. The baryon acoustic oscillations, or BAO, are the same acoustic waves frozen into the CMB, but now imprinted in the distribution of matter. The sound horizon, the distance acoustic waves could travel in the early plasma before recombination, is a preferred physical scale, roughly 150 megaparsecs in comoving distance today. Galaxies are slightly more likely to be separated by this distance than by nearby distances, and this statistical excess shows up as a subtle bump in galaxy correlation functions. Because the physical scale of the sound horizon is calculable from first principles, BAO acts as a standard ruler across cosmic distances, providing an independent way to trace the expansion history and test the cosmological model. Measuring BAO requires galaxy surveys covering enormous volumes. The signal is subtle, only a few percent above the background clustering level, and it can be washed out by various systematic effects if not carefully controlled. But it has been detected in multiple surveys with increasing precision, and the inferred distance scale matches the prediction from the CMB sound horizon with remarkable consistency. This consistency across completely different observational methods and physical scales is one of the hallmarks of a robust cosmological model. Gravitational lensing provides yet another probe. Massive objects curve spacetime and bend the paths of photons passing nearby, distorting the apparent shapes of background objects. By measuring the statistical distortion of galaxy shapes over large areas of sky, weak gravitational lensing surveys map the distribution of all matter, including dark matter, across cosmic history. The results are consistent with the matter content and clustering amplitude inferred from the CMB. Strong lensing by galaxy clusters creates dramatic arcs and multiple images of background galaxies, providing detailed measurements of cluster masses that agree with other mass estimates. All of these threads, expansion, CMB spectrum and anisotropy, light element abundances, large-scale structure, baryon acoustic oscillations, gravitational lensing, converge on the same consistent picture. The universe began in a hot, dense state, expanded and cooled, formed atoms at 380,000 years, built galaxies and clusters over billions of years, and is now dominated by dark energy that is accelerating the expansion. The model that captures this history, lambdictum, fits the data with a precision that would have seemed miraculous to cosmologists of a few decades ago. But precision in fitting a model is not the same as completeness of explanation. The model has parameters we measure but cannot derive. It has components we infer but cannot directly identify. And it has a formal beginning that may not be a genuine physical event, but rather a mathematical boundary beyond which the model's equations lose their validity. The most honest statement about the state of cosmology is that we have a spectacularly successful phenomenological model of the universe's history, combined with deep ignorance about the fundamental nature of its major ingredients and genuine uncertainty about the nature of its beginning. That is not a failure. That is science at its most alive, with the successes pointing clearly toward the next layer of questions, and the mysteries concentrated at exactly the places where new understanding is most needed. The question of what caused the Big Bang requires first being precise about what we mean when we say Big Bang. The popular image is of an explosion, a fireball launched into empty space from some central point. This image is wrong in almost every important way. There was no central point. There was no pre-existing empty space for an explosion to expand into. There was no moment of detonation in the way an explosion has a detonation. What the Big Bang model describes is the early state of the universe as a whole, a state that was hot and dense everywhere simultaneously, with no distinguished center and no exterior region. The expansion of the universe is not the spreading of matter through pre-existing space. It is the growth of space itself, a change in the metric that describes the geometry of everything. Every region of space was the center of the hot dense phase in the same sense that every point on the surface of an expanding balloon is the center of the expansion. There is no location that was the origin. The origin, if we use that word, was everywhere at once. This matters for causality. In ordinary experience, causes happen at places and at times. A cause is located somewhere, produces an effect somewhere else, and the effect follows the cause in time. But if the Big Bang is the origin of time itself, or at least of the time we can describe with our current theories, then the demand for a prior cause runs into a conceptual obstacle. If time did not exist before the Big Bang, there was no before in which a cause could operate. The question, what caused the Big Bang, may be asking for a cause to operate in a temporal framework that did not yet exist. This is not a rhetorical dodge. It is a genuine logical issue with deep roots in both physics and philosophy. General relativity treats time not as a fixed backdrop against which events occur, but as a dynamical component of spacetime, shaped by matter and energy, participating in the equations of motion. If time is part of the dynamical system rather than the stage on which the system plays out, then the origin of that system is also the origin of time, and causality, which is defined within time, has nothing to operate on. The question we want to ask might then need to be reformulated. Instead of asking what caused the Big Bang, we might ask what kind of physical or mathematical description accounts for the boundary conditions of the universe, including the fact that those boundary conditions specify an early hot dense phase with particular properties. We might ask whether the concept of causality can be extended or generalized to cover the regime where time itself is becoming, and what such an extension would look like. We might ask whether the initial conditions of the universe are determined by some deeper theory that does not require a temporal cause, a theory where the conditions arise as a logical or mathematical necessity rather than as the result of a prior event. These are genuine scientific questions, not just philosophical ones, because they have implications for what we would observe in the universe. Different proposals for the nature of the beginning predict different observable signatures, and those signatures can in principle be tested with current and future instruments. The territory is not outside science. It is at science's frontier, where the established framework runs out and new ideas are being proposed, tested, and refined. Before we go to those ideas, we need to sit with one more aspect of the evidence that changes what we are looking for. The universe is not only old and hot, it is almost astonishingly uniform on large scales, and that uniformity is itself a clue. The cosmic microwave background is the same temperature in every direction to 1 part in 100,000 after you remove the effects of our own motion through space. This means that regions of the sky that are on opposite sides of us, separated by the full width of the observable universe, have temperatures that differ by only a few dozen microkelvin. These regions have never been in causal contact in the standard Big Bang timeline. Light has not had time to travel from one to the other. They have had no opportunity to exchange energy or information and reach the same temperature by any direct physical interaction. This is the horizon problem, and it is a genuine puzzle about initial conditions. In the simplest hot Big Bang model, the early uniformity appears to be a brute fact, written into the initial conditions without explanation. Why did the universe start in this extraordinary state of near homogeneity? Why not in a chaotic, unequal state? The model does not say. It takes the homogeneity as given and evolves it forward, but taking something as given is not the same as explaining it. There is also the flatness problem. The universe is very close to spatially flat today. In the evolution of a hot Big Bang universe without special initial conditions, spatial curvature grows in relative importance over time. A universe that is slightly curved at early times will become more curved as it evolves. For the universe to appear as flat as we observe it today, it must have been extraordinarily flat at early times, fine-tuned to flatness at a level of roughly 1 part in 10 to the 60th at the Planck epoch. This is an extreme sensitivity of the present state to the initial conditions, and it begs for explanation. These puzzles do not invalidate the Big Bang model. They point to something missing in the story, some earlier chapter that set the hot dense phase into such an improbably ordered initial state. They motivate the search for a mechanism, a dynamical process that naturally produces the observed uniformity and flatness, without requiring them to be imposed by hand as initial conditions. That motivating role is what makes these puzzles scientifically productive rather than just philosophically uncomfortable. The hint of a mechanism comes from thinking about what kind of early process could create uniformity across what are now causally disconnected regions. One approach is to posit that those regions were actually in causal contact much earlier, that the universe's causal structure was different at some early time in a way that allowed information to propagate across what is now the full observable sky. Another approach is to propose that the initial conditions are not arbitrary, but are determined by some fundamental law that privileges the homogeneous flat state. Both approaches have been developed into concrete physical proposals, and we will examine them in detail in the chapters ahead. But the key point, standing here at the foundation of evidence, is that the uniformity and flatness of the universe are not merely aesthetic properties. They are quantitative constraints on the nature of the beginning, clues encoded into the present universe about what the earliest chapter must have looked like. The universe is speaking to us through these clues, not loudly, not in a language that is immediately transparent, but persistently and consistently. The CMB tells us the universe was uniform to 1 part in 100,000. The flatness measurements tell us the geometry is very close to Euclidean on the largest scales. The structure tells us the tiny deviations from uniformity have specific statistical properties, close to Gaussian, close to scale invariant, and every one of these properties is a message from the beginning, a fingerprint of the process that set the stage for everything we see. Reading that fingerprint is the project of early universe cosmology, and the tools we use to read it are theories of what could have preceded the hot dense phase, theories that must not only explain the uniformity and flatness, but must also predict specific observable signatures that we can search for with current and future instruments. The theories are bold and some of them are strange, and none of them is fully established. But they are scientific theories in the proper sense. They make testable predictions, they engage with the data we have, and they can be ruled out. The evidence has taken us to the edge of what we can see. In the chapters ahead, we cross that edge and ask what lies beyond. To understand what the beginning might have been, we have to do something that feels almost violent to ordinary intuition. We have to run time backward. Not metaphorically, not as a thought experiment we can dismiss when it gets uncomfortable, but as a rigorous physical exercise using the equations that govern the universe's evolution and following them as far back as they remain trustworthy, and then being honest about where they stop being trustworthy and why. The universe we inhabit today is approximately 13.8 billion years old, a number determined by fitting the cosmological model to the CMB, large-scale structure, and expansion history simultaneously. It is a number we know with a precision that would have seemed impossible 2 generations ago. The expansion rate, the matter content, the dark energy density, the primordial fluctuation spectrum, all of these parameters are now measured well enough to pin down the age with an uncertainty of less than 1%. 13.8 billion years. That is how long the universe has been evolving from the hot, dense state we call the Big Bang. But those 13.8 billion years are not a uniform stretch of time. Different eras had radically different physics, different dominant components, different scales of structure, different rules for what could exist. Running the timeline backward is not simply watching a movie in reverse. It is moving through a sequence of phase transitions and regime changes, each one altering the character of the universe more profoundly than the last, until we reach a boundary where the physics we know breaks down entirely and something else, something we do not yet fully understand, must take over. The journey backward begins gently. We are right now in the era of dark energy domination. The expansion is accelerating. Galaxies are still forming stars, though the peak of cosmic star formation was billions of years ago, and the rate has been declining since. The cosmic web is essentially in place. The largest structures have stopped growing significantly because dark energy is pulling the universe apart faster than gravity can pull matter together on those scales. We live in a universe that is, in a sense, beginning to fossilize, its structure locked in as the accelerating expansion stretches everything apart, and the last stars eventually burn out over timescales that make the current age of the universe look brief. Rewind past the present, and through the first few billion years, and the universe looks busier. Galaxies are closer together. The expansion rate was slower because dark energy had not yet come to dominate. Matter was denser, gravity was more effective at pulling things together, and the rate of galaxy mergers and interactions was higher. The first galaxies formed within the first billion years after the hot dense phase, assembling from the dark matter halos that had been building since recombination. The first stars lit up the universe after what cosmologists call the cosmic dark ages, a period after recombination when the universe was filled with neutral hydrogen, but no light sources yet existed. Those first stars are a frontier of observation and theory simultaneously. The James Webb Space Telescope has been pushing back our view of galaxy formation to within a few 100 million years of the Big Bang, finding galaxies that are surprisingly massive and mature for their age in ways that challenge some models of early galaxy formation. These findings are not a crisis for the Standard Model, but they are reminders that the details of how structures assembled are not fully understood and that early epochs still hold surprises. Continue rewinding past galaxy formation, past the ignition of the first stars, past the reionization of the universe, when ultraviolet light from the first sources broke apart the neutral hydrogen that had formed at recombination. Rewind through the cosmic dark ages, a time when the universe was opaque to ultraviolet light but transparent to the CMB photons. Rewind to recombination itself, 380,000 years after the hot phase began, when neutral atoms formed and the CMB was released. Before recombination, the universe is a plasma. Photons and charged particles are coupled into a single fluid. The behavior of this fluid is well understood from plasma physics and radiation transport. The acoustic oscillations we see frozen into the CMB are driven by the physics of this plasma era. The equations governing the plasma are tested and precise. The CMB power spectrum we observe today is a prediction of these equations that has been verified to extraordinary accuracy. We are on solid ground here. The physics is well established. The uncertainties are systematic and quantifiable. Rewind further, past recombination, and through the first few thousand years. The universe is still dominated by radiation at this epoch, a hot, dense bath of photons and relativistic particles. The transition from radiation domination to matter domination happened at a red shift of roughly 3,400, when the energy density in matter finally exceeded the energy density in radiation, as expansion diluted them at different rates. Before that transition, the expansion was driven by radiation, and the growth of structure was suppressed compared to the matter-dominated era that followed. This transition matters for structure formation, because dark matter could begin clumping during the radiation-dominated era, building up potential wells that baryons later fell into, but the growth was slower and more complicated than in the matter-dominated era. The details of structure growth across this transition leave imprints in the matter power spectrum that we measure in galaxy surveys, providing another consistency check on the model. Push back past matter radiation equality, and the universe becomes simpler in its composition, but more extreme in its conditions. Temperature is rising rapidly as we rewind. At a redshift of about 1 million, corresponding to a few tens of thousands of years after the hot phase began, the temperature was roughly 30,000 Kelvin. Still a plasma, still radiation-dominated, but with the electrons and ions beginning to have individual identities rather than the more exotic identities they had at even earlier times. The physics here is conventional atomic and plasma physics pushed to high temperatures, and the equations are well tested. Rewind to the first minutes and you reach the era of Big Bang nucleosynthesis. The temperature is now measured in billions of Kelvin. Typical photon energies are in the MeV range, comparable to nuclear binding energies. Free protons and neutrons exist in a balance set by the weak interaction rates and the expansion rate. As the universe cools through this era, the weak interactions freeze out, the neutron-to-proton ratio locks in, and the subsequent assembly of helium nuclei proceeds on a timescale of minutes. The physics of this era is nuclear and weak interaction physics, tested in laboratories with precision experiments. The neutron lifetime, the cross-sections for nuclear reactions, the rates of weak processes, all of these are measured quantities that feed directly into the nucleosynthesis calculations. The resulting predictions for light element abundances, which match the observations well for deuterium and helium, are a triumph of the connection between cosmology and particle physics. We are looking at the universe a few minutes after the hot phase began and describing it with physics we have tested on Earth. Go back further, past nucleosynthesis to the first seconds. Now we are in genuinely extreme territory. The temperature is tens of billions of Kelvin, the energy density is enormous, and the universe is a dense plasma of particles and antiparticles in near thermal equilibrium. Electrons, positrons, photons, neutrinos, and small numbers of protons and neutrons all exist together, constantly creating and annihilating each other as long as the temperature provides sufficient energy for pair creation. At around 1 second after the hot phase began, neutrinos decouple from the plasma. The weak interaction rate, which couples neutrinos to electrons and positrons, falls below the expansion rate, and neutrinos begin streaming freely without further interaction. This neutrino decoupling is a freeze-out process, and it leaves behind a cosmic neutrino background analogous to the CMB, but much harder to detect because neutrinos interact only through the weak force. The cosmic neutrino background has not been directly detected in the way the CMB has been, but its existence is inferred from its gravitational effects on structure formation and on the CMB, and those inferences are consistent with the standard picture. Shortly after neutrino decoupling, the universe cools below the threshold for electron-positron pair creation. Electrons and positrons annihilate faster than they are created, and the energy from their annihilation heats the photon bath slightly relative to the neutrinos, which have already decoupled and do not share in this heating. The result is a specific temperature ratio between photons and neutrinos that persists to the present day, a precise prediction of standard cosmology that is confirmed indirectly through its effects on the CMB power spectrum and nucleosynthesis. These early seconds are well described by the standard model of particle physics applied to hot, dense plasma. The relevant physics is known, tested in accelerators, and extrapolated to cosmological conditions with confidence. The uncertainties at this stage are real but manageable, and the predictions are specific enough to test. But as we push further back, the familiar comfort of tested physics begins to erode. We are approaching energies that no terrestrial experiment has directly reached, and the extrapolation from tested physics into this regime carries increasing uncertainty. At around 1 microsecond after the hot phase began, the temperature is around 2 trillion Kelvin, and the energy scale is around 1 GeV, the scale of proton and neutron rest masses. Above this temperature, protons and neutrons are not the relevant degrees of freedom. Instead, quarks and gluons exist in a deconfined state, a quark-gluon plasma rather than the bound states we call hadrons. The transition between the hadronic phase we live in now and the quark-gluon plasma phase of the early universe is called the QCD phase transition, named for quantum chromodynamics, the theory that describes the strong nuclear force. The QCD phase transition has been studied extensively in heavy ion collision experiments at facilities like the Relativistic Heavy Ion Collider at Brookhaven National Laboratory and the Large Hadron Collider at CERN. By colliding heavy nuclei at extreme energies, physicists can briefly recreate conditions similar to those of the early universe at this epoch and study the properties of the quark-gluon plasma. The results have been surprising in some ways. The quark-gluon plasma is not a simple weakly interacting gas of quarks and gluons as originally expected, but a strongly coupled fluid with very low viscosity, behaving more like a near-perfect liquid than a gas. Understanding this state has required sophisticated theoretical tools, and the work is ongoing. For cosmology, the QCD transition matters because it changes the effective number of degrees of freedom in the early universe plasma, which affects the expansion rate, the timing of other transitions, and the nature of matter at that epoch. It is also relevant to the origin of the baryon asymmetry, the excess of matter over antimatter that resulted in a universe made of matter rather than nothing. We will return to that asymmetry because it is one of the deepest unsolved problems in all of physics, and it sits squarely in the territory we are exploring. The effective number of degrees of freedom is a parameter that captures how many distinct types of particles and fields are contributing to the energy density at a given temperature. As we go back in time and the temperature rises, new particle species become thermally accessible, and the number of degrees of freedom increases in steps. Each step changes the relationship between temperature and energy density, and those changes feed into the expansion rate through the Friedmann equations. The standard model of particle physics predicts how these degrees of freedom evolve with temperature, and the predictions are tested by comparing with nucleosynthesis and CMB observations. At energies somewhat above the QCD scale, around 100 GeV, we enter the regime of the electroweak phase transition. Below this energy, the electromagnetic and weak nuclear forces appear as distinct, separate forces with different carriers and different strengths. Above this energy, they are unified into a single electroweak force described by a single gauge symmetry. The symmetry breaking that separates them at lower energies is associated with the Higgs field acquiring a non-zero vacuum expectation value, a process that also gives masses to the W and Z bosons and to the fundamental fermions through their Yukawa couplings to the Higgs. The Higgs mechanism is no longer speculation. The discovery of the Higgs boson at the Large Hadron Collider in 2012 confirmed that the Higgs field exists and that its mass is around 125 GeV, a value consistent with the Standard Model's predictions. The Higgs boson's mass is not an arbitrary parameter, but a measured quantity that has immediate implications for the stability of the electroweak vacuum and for the nature of the electroweak phase transition in the early universe. Whether the electroweak phase transition was a smooth crossover or a sharp first-order transition matters enormously for cosmology because a first-order transition would proceed through bubble nucleation and would create conditions far from thermal equilibrium, which is one of the Sakharov conditions for generating a baryon asymmetry. Calculations based on the observed Higgs mass suggest that in the Standard Model, the electroweak transition is actually a smooth crossover rather than a first-order phase transition, which means the Standard Model alone cannot generate the observed baryon asymmetry at the electroweak scale. This pushes the explanation for matter-antimatter asymmetry either to higher energies or to physics beyond the Standard Model. The electroweak scale sits at the frontier of what has been directly tested in laboratory experiments. The Large Hadron Collider operates at center-of-mass energies of up to 13 or 14 TeV, corresponding to temperatures of roughly 10 to the 17th Kelvin, and this is where our experimental reach currently ends. The physics beyond this scale, the physics that describes the universe at earlier and hotter times, is extrapolated from theoretical frameworks that have not been directly tested. Going beyond the electroweak scale into the regime of grand unification, if grand unification occurs, the three non-gravitational forces of the Standard Model, the strong nuclear force, the weak nuclear force, and electromagnetism, might unify into a single force described by a larger symmetry group. Grand unified theories predict the existence of additional force carriers, new types of matter, and the eventual instability of the proton, among other things. Proton decay has been searched for in enormous underground detectors and has not been observed, placing strong constraints on the simplest grand unified theories. More complex versions survive those constraints, but none has been confirmed. Grand unification also predicts the production of magnetic monopoles in the early universe, as we noted earlier. These are topological defects that arise when the grand unified symmetry breaks to the Standard Model symmetry at lower temperatures. Their absence in observations is one of the motivations for inflation, because inflation can dilute any pre-existing monopole density to negligible levels by vastly expanding the volume of the observable universe. The energy scale of grand unification is typically around 10 to the 15th or 10 to the 16th GeV, roughly 12 orders of magnitude above what accelerators can currently reach. This means the physics at that scale is constrained by theoretical consistency and by indirect cosmological observations rather than by direct laboratory tests. The further we extrapolate beyond tested physics, the more important it becomes to identify which features of our models are robust and which depend on assumptions that could be wrong. As we push back further toward the beginning, the temperature continues to rise and the energy scale approaches the Planck scale, roughly 10 to the 19th GeV, the scale at which quantum gravitational effects become important. This is the scale where the energy in a quantum of radiation becomes comparable to the energy of a black hole of the same wavelength, where quantum fluctuations of spacetime itself become as important as the matter and radiation fields. Below the Planck scale, we can treat spacetime as a smooth classical background on which quantum fields propagate. At and above the Planck scale, that separation breaks down entirely. The Planck time, roughly 10 to the minus 43 seconds, is not an arbitrary number. It is the time you get when you combine the three fundamental constants of quantum gravity: Newton's gravitational constant g, Planck's constant h-stroke, and the speed of light c, into a combination with dimensions of time. Similarly, the Planck length is roughly 10 to the minus 35 meters, and the Planck energy is roughly 10 to the 19th GeV. These are not merely very small and very large numbers. They mark the boundary of the regime where our current theoretical frameworks are expected to fail. Before the Planck time, extrapolating the classical Friedmann equations of general relativity gives diverging densities and curvatures. The scale factor of the universe, the parameter that describes how much space has expanded, formally goes to zero. The temperature formally goes to infinity. These divergences are what we call the initial singularity, and it appears in every classical model of the Big Bang. It is a statement that if you run general relativity backward in time, the universe collapses to a point at a finite time in the past. But we should not take this singularity literally. Mathematical divergences in physical theories are almost always signals of missing physics, not genuine infinities in nature. When classical electrodynamics produced infinities for the self-energy of a point charge, it was telling us that classical electrodynamics alone was incomplete, and quantum electrodynamics provided the resolution. When general relativity predicts a singularity inside a black hole, it is telling us that classical general relativity is incomplete in that regime, and a full theory of quantum gravity would presumably resolve it. Similarly, the cosmological singularity is almost certainly a signal that a quantum theory of gravity would describe the Planck epoch very differently from classical general relativity. The singularity theorems of Roger Penrose and Stephen Hawking, proved in the 1960s and 1970s, established that singularities are a generic prediction of classical general relativity under certain reasonable energy conditions. These theorems are mathematically rigorous, and they demonstrate that the singularity is not an artifact of assuming perfect symmetry in the initial conditions. Under very general conditions, any classical spacetime satisfying Einstein's equations with positive energy densities will contain singularities. This is a powerful result, but it is also a result about a classical theory, and it says nothing about what a quantum theory of gravity would predict at the same scales. The singularity theorems tell us that classical general relativity inevitably breaks down near the beginning, not that the universe literally had a singular beginning. They mark the boundary of the classical description. What lies on the other side of that boundary requires quantum gravity. This is where the deep difficulty lies. We do not have a complete, tested, generally accepted theory of quantum gravity. We have serious candidates, frameworks that have been developed over decades with great mathematical sophistication, but none of them has made predictions that have been confirmed by experiment in a way that definitively establishes them as the correct description of quantum gravity. The leading candidates are string theory and loop quantum gravity, and they approach the problem from very different starting points. String theory replaces point particles with one-dimensional extended objects, strings, whose different vibrational modes correspond to different particles. By incorporating supersymmetry and extra dimensions, string theory achieves a consistent quantum theory that includes gravitational interactions. It has produced some remarkable results, including insights into black hole thermodynamics and the ADS-CFT correspondence, which relates a theory of gravity in a negatively curved space to a non-gravitational quantum field theory on its boundary. But it has not yet produced an unambiguous cosmological prediction that could be tested with current instruments, and the landscape of possible solutions in string theory, the vast space of different possible vacuum states with different low-energy physics, raises difficult questions about whether the theory predicts anything specific at all. Loop quantum gravity takes a different approach, quantizing spacetime geometry directly rather than starting from particle physics and adding gravity. It predicts that space is not continuous but discrete at the Planck scale, with area and volume taking on quantized values. It has been applied to cosmological settings in a framework called loop quantum cosmology, which we will discuss in detail later. Loop quantum gravity has produced specific predictions for quantum corrections to the behavior of the universe near the Planck scale, including the possibility of a bounce that replaces the classical singularity. But it also faces challenges in connecting its Planck scale predictions to the low-energy physics we observe, and the mathematical challenges of the full theory remain formidable. Other approaches to quantum gravity include causal set theory, which models spacetime as a discrete set of events connected by causal relations, and causal dynamical triangulations, which constructs quantum spacetime from building blocks assembled according to causal rules. These approaches share the idea that spacetime must be fundamentally discrete or combinatorial at the Planck scale, arising from some deeper structure that does not presuppose a smooth continuum. What these approaches share is the recognition that the classical notion of spacetime as a smooth four-dimensional manifold almost certainly breaks down at the Planck scale. What replaces it is different in different frameworks, but the common message is that the Planck epoch is not just hot and dense in the ordinary sense. It is a regime where the very concepts of space, time, and geometry, as we understand them, may not apply, or may apply only as emergent approximations to something fundamentally different. This has profound implications for the question of what caused the Big Bang. If time itself is an emergent concept that arises from some deeper, more fundamental description of the Planck epoch, then asking what caused the universe to begin is asking for a cause that must operate in a temporal framework that did not yet exist as a fundamental feature of reality. The question might be well posed within the emergent description, but have no analog in the fundamental description. It might be like asking what is north of the North Pole, a question that is grammatically correct but geometrically empty. Or the question might be translatable into the language of the deeper theory, where it takes a different form. Instead of asking for a prior cause, we might ask for a boundary condition, a mathematical condition that determines what the universe looks like at the edge of the regime where classical spacetime applies. Instead of asking for a temporal trigger, we might ask for a principle that selects which quantum gravitational state the universe started in. These are different kinds of questions than causal ones, but they may be the right questions for the regime we are dealing with. To get a sense of how these questions arise concretely, it helps to look at how general relativity already changes our understanding of time and causality, even before we add quantum mechanics. Einstein's insight was that time is not a universal background parameter ticking away regardless of what happens. Time is part of the spacetime manifold, and the geometry of that manifold, including the geometry of time, is determined by the matter and energy content through Einstein's field equations. This means that different observers can have different rates of time passage, not just as a perceptual effect, but as a physical fact. A clock near a massive object runs slower than a clock far from it. A clock in motion runs slower than a stationary one. These effects are measured in everyday technology. GPS satellites require corrections for both special and general relativistic time dilation to maintain the accuracy that makes navigation possible. Time is not the same for everyone, and it is not a fixed background. It is part of the dynamical system described by general relativity. In cosmology, this dynamical nature of time has a specific consequence. The time coordinate we use to describe cosmic history is not a pre-existing container in which the universe exists. It is defined by the geometry of spacetime, which in turn is determined by the matter and energy content through the Friedmann equations. When we say the universe is 13.8 billion years old, we are saying that the proper time elapsed along a geodesic, a free-falling path, since the hot dense phase is 13.8 billion years. This is a well-defined physical quantity, but it presupposes a well-defined spacetime geometry, which presupposes that general relativity is valid. At the Planck epoch, if spacetime is not a smooth classical manifold, but something more fundamental, the time coordinate may not be well defined in the same sense. The Planck time is not just a very early moment in a pre-existing timeline. It may be a boundary beyond which the concept of a moment, of a definite time with a definite geometry, breaks down. What replaces it is unknown, but whatever it is, it does not obviously support the temporal framework within which causal questions are normally asked. This is why the singularity is philosophically as well as mathematically important. It is not just a technical divergence to be regularized by quantum corrections. It is a signal that the conceptual framework we use for asking about beginnings and causes may not apply at the boundary of what the framework can describe. The singularity is where general relativity waves a white flag and admits that something else must take over, and that something else may operate by different rules than the ones that make causal questions sensible. With this understanding of why the singularity matters and what it does not mean, we can look at what the most robust physical considerations tell us about the very early universe, before we get into the specific proposals for what happened at or before the Planck epoch. One of the most important constraints comes from thermodynamics, specifically from the concept of entropy. The second law of thermodynamics states that the entropy of a closed system cannot decrease over time. Entropy is a measure of disorder, or more precisely, of the number of microstates compatible with the macroscopic state of a system. A system with high entropy has many possible microscopic arrangements consistent with its observable properties. A system with low entropy has few. The striking fact about the early universe is that it had extremely low entropy despite being in thermal equilibrium and having extremely high temperature and density. This seems paradoxical because thermal equilibrium is usually considered a high entropy state. The resolution is that when gravity is important, the notions of equilibrium and entropy are different from those in conventional thermodynamics. A smooth, uniform distribution of matter is not the highest entropy state when gravity is included. Gravity is attractive, and it can lower the energy of the system by pulling matter together. The highest entropy state of a self-gravitating system is not a uniform gas but black holes. Clumped matter in black holes has far higher entropy than the same matter spread uniformly. This means that the early universe, despite its thermal uniformity, was in a state of extremely low gravitational entropy. It was ordered in the sense that matters for the arrow of time, smooth rather than clumped, uniform rather than structured with black holes. As the universe evolved and gravity pulled matter into structures, galaxies, stars, and eventually black holes, gravitational entropy increased. The second law was satisfied not by conventional thermodynamic processes, but by the growth of gravitational clumping. The physicist Roger Penrose has argued that this low initial entropy of the early universe is one of the most remarkable and unexplained features of nature, and that any theory of the Planck epoch must account for it. The odds of a randomly chosen initial condition of the universe being as smooth and ordered as the early universe appears to have been are, by Penrose's calculation, fantastically small. The initial state must have been chosen from an extraordinarily narrow range of possibilities if we are to explain the low initial entropy through chance. This argument does not prove that a specific theory of the beginning is correct, but it establishes a sharp constraint that any such theory must meet. It must explain not just the existence of a hot, dense early phase, but the specific smoothness and low entropy of that phase. It must explain why the universe started in such an ordered state when almost all possible initial states are disordered. This is the problem of the arrow of time dressed in cosmological language, and it is no easier to solve at cosmological scales than it is in everyday thermodynamics. Some proposals address this by arguing that the initial smooth state is not improbable, but rather mandatory, required by the laws of quantum gravity, or by a no-boundary principle that makes smooth beginnings the only consistent quantum gravitational starting points. We will examine those proposals in detail. Others argue that the arrow of time is a selection effect, that only in universes with low initial entropy can complex structures and observers arise, so we should not be surprised to find ourselves in such a universe. We will examine those arguments too, along with their difficulties. The key point here is that the low entropy of the early universe is a real quantitative puzzle, not a vague philosophical question. Any theory of origins must grapple with it, and theories that explain it naturally earn credit that theories requiring it as an unexplained assumption do not. There is another remarkable feature of the early universe that deserves attention before we turn to inflationary cosmology: the near-perfect scale invariance of the primordial fluctuation spectrum. The density perturbations that seeded all of cosmic structure have a specific statistical property. Their amplitude is almost the same across a vast range of physical scales. Small-scale perturbations and large-scale perturbations have nearly equal strength, modulated by a gentle tilt that departs from perfect scale invariance by a few percent. This scale invariance, first proposed by Harrison and Zeldovich independently in the early 1970s, is not something that follows from the hot Big Bang itself. In a simple hot Big Bang without additional early physics, there is no natural scale to set the perturbation amplitude or to make it scale invariant. You would have to impose the scale invariant spectrum as an initial condition, and you would have no explanation for why that particular initial condition was chosen. Scale invariance turns out to be a natural output of a process that generates perturbations while the universe is in a state of quasi-exponential expansion. During such expansion, there is a constant rate of stretching of wavelengths, and this constant rate, combined with the quantum mechanics of fields in de Sitter spacetime, naturally produces a spectrum that is close to scale invariant. This is one of the most powerful motivations for inflationary cosmology. It transforms an unexplained initial condition into a prediction of a dynamical process. The slight departure from perfect scale invariance, quantified by the spectral index NS, which current measurements pin at approximately 0.965, is itself informative. Perfect scale invariance would give NS equal to 1. The measured tilt tells us about how the inflationary process was changing as the perturbations we observe today were being generated. Different models of the inflationary mechanism predict different values of NS, and the measured value already rules out some models and constrains others. This is what makes the primordial spectrum such a powerful cosmological probe. It is not just a description of the initial conditions. It is a fossil of the process that created those conditions. Reading the spectrum carefully, measuring NS to ever greater precision, looking for departures from Gaussianity, searching for the gravitational wave signal that different models predict, all of these are ways of interrogating the mechanism of the beginning rather than simply accepting the beginning as given. Before turning to inflation in detail, it is worth pausing to reflect on the overall structure of the argument so far, because that structure shapes everything that follows. We have established that the universe has a well-measured history beginning from a hot dense phase roughly 13.8 billion years ago. We have multiple independent lines of evidence, all converging on the same early state. We have a theoretical framework, lambdictum, that fits this evidence with remarkable precision using a small number of parameters. We have also established that this framework has limits. It breaks down at the Planck scale. It includes components whose fundamental nature is unknown. It rests on initial conditions, the smoothness, flatness, and near-scale invariant perturbation spectrum of the early universe, that are not explained within the framework itself but are imposed from outside. And it points toward a singularity that is a warning, not a destination. The natural scientific response to a successful but incomplete framework is to look for a deeper framework that explains what the successful one takes as given. This is what inflationary cosmology attempts to do for the initial conditions of the hot Big Bang, and this is what quantum gravity attempts to do for the breakdown at the Planck scale. Neither attempt is complete, but both are genuine scientific enterprises making specific predictions that can be tested against observations. The connection between the two attempts is crucial. Inflation, if it occurred, did not happen in a vacuum outside of physics. It happened in the Planck-era universe or just after, driven by fields whose behavior at those energies is constrained by the same quantum gravitational considerations that determine what happened at the singularity. Complete theory of the beginning must somehow integrate the dynamics of inflation with the quantum physics of the Planck epoch, and doing so requires tools we are still developing. What we can do now is examine inflation as a framework for extending the story of the early universe, asking what it explains and what it leaves unexplained, what it predicts and what those predictions look like in the data we have and the data we are working to collect. And we can ask, honestly and without premature closure, what lies at the boundary of inflation itself. Because inflation, powerful as it is not the ultimate beginning. It requires initial conditions of its own, and those conditions take us back to the edge where quantum gravity must speak. The flatness problem is sometimes presented as a philosophical puzzle, but it is important to understand how sharply it can be quantified, because the sharpness is what makes it a genuine scientific problem rather than an aesthetic preference. In the Friedman equations, the evolution of spatial curvature relative to the total energy density depends on how the scale factor grows. For a matter-dominated universe, the curvature term grows as the scale factor squared. For a radiation-dominated universe, it also grows with expansion. This means that if the universe is even slightly curved at early times, that curvature becomes increasingly significant as the universe expands and ages. Working backwards from the present-day constraint that the universe is flat to within a few percent, and extrapolating to the Planck time when the universe was 10 to the minus 43 seconds old, the curvature at that time must have been vanishingly small, at most around 1 part in 10 to the 60th of the total energy density. This is not a small adjustment. It is an extraordinary fine-tuning. The universe at the Planck scale would have had to be flat to 60 decimal places to arrive at the flatness we observe today. There is no known reason within classical cosmology why the universe would have been set up this way. This kind of fine-tuning is what physicists call a hierarchy problem or a naturalness problem. It is not logically impossible for the universe to have been that flat at the Planck time, but in the absence of a mechanism that naturally produces that flatness, it looks like a coincidence of cosmic proportions, a coincidence that demands explanation. Inflation resolves this by changing the dynamics. During exponential expansion, the curvature term in the Friedman equations decays rapidly relative to the dominant vacuum energy. Even if the universe had significant curvature before inflation began, the exponential growth of the scale factor during inflation would have diluted the curvature to negligibility. The longer inflation lasted, the closer the universe would have been to flat when inflation ended, regardless of its initial curvature. Inflation does not require the universe to start flat. It drives the universe toward flatness dynamically, making the observed flatness a prediction rather than a coincidence. The same basic mechanism resolves the horizon problem. During exponential expansion, the physical size of a region grows much faster than the Hubble radius, the scale that characterizes causal contact. A region that was in causal contact before inflation, small enough to have exchanged signals and equilibrated, can be stretched by inflation into a region much larger than the observable universe. What appears to be disconnected, causally isolated regions today were actually in contact before inflation and acquired their near-uniform temperature through ordinary physical processes in that earlier intimate phase. The key is the relationship between the Hubble radius and the scale factor during inflation. In a matter-dominated or radiation-dominated universe, the comoving Hubble radius grows with time, meaning causal contact extends further and further. But during inflation, the comoving Hubble radius shrinks with time, meaning modes that were once within the causal contact radius are being pushed outside it. This is the stretching that makes previously contacted regions appear disconnected in the late universe. Running inflation backward, those disconnected regions were once inside a single causal patch, and their uniformity is a memory of that earlier phase. Inflation's resolution of the monopole problem is even more straightforward. If any heavy relics, whether magnetic monopoles, cosmic strings, or other topological defects, were produced before or during the very early stages of inflation, the exponential expansion of space dilutes their number density so drastically that they become essentially absent from the observable universe. Even if the initial density of monopoles were 1 per Planck volume, the exponential factor in inflation can reduce this to far less than 1 per observable universe. The absence of monopoles and other relics is therefore not a surprise in an inflationary universe. It is an automatic consequence of the dilution. But these three solutions, to the horizon, flatness, and monopole problems, are qualitative. They tell us that inflation can solve these problems, but they do not tell us how to distinguish inflation from other possible solutions. Any mechanism that dramatically expands the causal contact region of the early universe and dilutes unwanted relics would accomplish the same thing. The specific quantitative predictions that make inflation testable come from a fourth feature, the generation of primordial perturbations. Here inflation does something qualitatively different from simply resolving the three classical problems. It makes a genuine prediction about the statistical properties of the density fluctuations that seeded cosmic structure, a prediction that was not imposed, but emerges from the dynamics of quantum fields in an exponentially expanding spacetime. The mechanism works through a combination of quantum mechanics and the geometry of de Sitter space, the spacetime that describes an exponentially expanding universe. In ordinary flat spacetime, quantum fluctuations of a field have a specific vacuum state, and the fluctuations at different scales are uncorrelated with each other. In de Sitter space, the situation is different. The exponential expansion stretches wavelengths, taking quantum fluctuations from microscopic scales and stretching them to macroscopic and eventually superhorizon scales. As a mode's wavelength grows beyond the Hubble radius, it can no longer oscillate because information cannot propagate across it fast enough. The mode freezes out, and its amplitude at the time of horizon crossing becomes a fixed, classical perturbation imprinted on the background geometry. This process converts quantum uncertainty into classical structure. The indeterminacy of a quantum field's vacuum fluctuations becomes, after stretching and freezing, a definite but randomly distributed pattern of density variations. These density variations are the seeds of all cosmic structure. Galaxies exist because inflation imprinted density variations in the early universe that gravity later amplified into the structures we observe. The predicted spectrum has specific properties. It is nearly scale invariant because the quasi-exponential expansion proceeds at nearly the same rate for modes of different wavelengths as they cross the horizon. It is Gaussian to high accuracy because the fluctuations arise from a free quantum field in its ground state, and free quantum fields have Gaussian statistics. And it is adiabatic, meaning that the fluctuations are in the energy density of all species simultaneously rather than being fluctuations in the relative composition. These three properties, near-scale invariance, Gaussianity, and adiabaticity, are predictions of single-field slow-roll inflation, and they have all been confirmed by CMB observations. The near-scale invariance is perhaps the most striking confirmation. The spectral index NS is measured to be approximately 0.965, less than 1 by about 3.5%. This deviation from perfect scale invariance, called the tilt, is itself a prediction of inflation. In realistic inflation models, the inflationary energy is not perfectly constant, but changes slightly as the inflatoned field rolls along its potential. This slow change produces a slight tilt in the spectrum, with larger scales having slightly more power than smaller scales. The measured tilt is consistent with the simplest slow-roll inflationary models. Gaussianity is tested through the higher-order statistics of the CMB temperature field. A perfectly Gaussian field has no 3-point or higher correlations beyond what the 2-point function determines. Departures from Gaussianity, called non-Gaussianity, can arise in models with multiple fields or with non-canonical kinetic terms. The Planck satellite measured the CMB with sufficient precision to constrain non-Gaussianity at a level that rules out many alternative models. Single-field slow-roll inflation predicts non-Gaussianity that is suppressed by slow-roll parameters, too small to detect with current instruments. The absence of detectable non-Gaussianity in the Planck data is consistent with the simplest inflationary models and rules out a range of alternatives. Adiabaticity is tested through the detailed shape of the CMB power spectrum and through the relationship between CMB and matter fluctuations. Adiabatic perturbations produce a specific pattern of acoustic peaks in the CMB that differs from what isocurvature perturbations, fluctuations in relative composition rather than total density, would produce. The observed CMB power spectrum is consistent with predominantly adiabatic perturbations, with tight upper limits on any isocurvature component. These confirmations have given inflation significant empirical support, but they are not yet decisive because the predictions that have been confirmed, near-scale invariance, Gaussianity, and adiabaticity, are shared by many inflationary models and also by some alternatives to inflation. To distinguish between models and to test inflation more stringently requires looking at the predictions that are more model-specific. The most important model-specific prediction of inflation is the gravitational wave background. Inflation does not only produce scalar perturbations, density fluctuations, through quantum fluctuations of the inflatoned field. It also produces tensor perturbations, gravitational waves, through quantum fluctuations of spacetime geometry itself. These primordial gravitational waves are a direct product of quantum gravitational physics in the inflationary era, and detecting them would be a window into physics at the energy scale of inflation. The amplitude of the primordial gravitational wave background relative to the scalar perturbations is characterized by the tensor scalar ratio R. This ratio depends on the energy scale of inflation. The higher the inflationary energy scale, the larger R for large field inflation models, where the inflatoned field traverses distances in field space comparable to the Planck scale. The tensor scalar ratio is large enough to be potentially detectable. For small field models, the ratio may be too small to detect with foreseeable instruments. The primordial gravitational wave background would leave a distinctive imprint in the polarization of the CMB. In particular, it would produce a pattern of B-mode polarization that cannot be generated by scalar perturbations alone. B-modes from primordial gravitational waves would appear on large angular scales, corresponding to physical scales larger than the horizon at recombination, and they would have a specific spectral shape that distinguishes them from other sources of B-mode polarization. The search for primordial B-mode polarization is one of the most important observational programs in cosmology. The challenge is severe. The primordial signal is potentially very faint, and it must be separated from two significant foreground sources of B-mode polarization. The first is polarized emission from dust in our own galaxy, which is significant over much of the sky and must be characterized through multifrequency observations. The second is gravitational lensing, which converts some of the E-mode polarization of the CMB into B-modes as photons pass through the gravitational fields of galaxies and dark matter along their path to our detectors. This lensing B-mode signal has been detected and measured, and it must be subtracted, a process called delensing, to reveal any primordial signal beneath it. A claim by the BICEP-2 experiment in 2014 of a detection of primordial B-modes was ultimately attributed to galactic dust contamination after joint analysis with Planck data. This episode illustrated both the difficulty of the measurement and the rigor required to establish a genuine detection. Since then, the BICEP and Keck array collaborations have continued to set increasingly stringent upper limits on R, currently below about 0.36 at 95% confidence. This limit rules out the simplest large-field inflation models, including the original quadratic potential that Lind proposed in chaotic inflation. It pushes allowed models toward those with smaller tensor-to-scalar ratios, which tend to have flatter potentials and more subtle dynamics. The next generation of CMB polarization experiments, including the Simons Observatory and CMB-S4, aim to push the sensitivity to R below 0, 1, or even low. At these levels, many of the surviving inflationary models would either be detected or definitively ruled out. If primordial B-modes are detected, the measurement of R would pin down the energy scale of inflation and provide a window into physics at that scale. If B-modes are not detected even at the sensitivity of CMB-S4, many of the most natural inflationary models would be under severe pressure. The interplay between the measured spectral index and the upper limit on R is particularly informative. In the space of NS versus R, different inflationary models predict different combinations, tracing out curves as the model parameters vary. The observational constraints from Planck and BICEP-Keck have already eliminated large regions of this parameter space, leaving surviving models clustered in a region that favors plateau-like potentials, where the inflated field rolls slowly along a nearly flat potential. The Starobinsky model and the Higgs inflation model are two examples that predict values of NS and R in the currently favored region. This observational pressure on inflationary model space is both exciting and humbling. It is exciting because it means we are making progress in identifying what kind of inflationary process is consistent with the data. It is humbling because the surviving models tend to be those where the potential is simple in a specific mathematical sense, but lacks a compelling derivation from fundamental physics. We can describe what kind of potential fits the data, but we cannot yet derive that potential from a first principles theory of the fundamental interactions. The concept of the inflated field deserves more careful treatment than it often receives in popular accounts, because the language of a field rolling down a potential can suggest a level of familiarity and simplicity that is misleading. We do not know what the inflaton is. We do not know which known particle or field plays its role, or whether it is a new, as yet undetected field that has no other role in physics. We can describe its properties, how slowly it must roll, what its potential must look like, how its quantum fluctuations must behave, but we cannot identify it with anything in our tested theories. The inflaton field is constrained to have certain properties by the CMB observations. Its potential must be flat enough to allow slow roll for the roughly 60 e-folds of exponential expansion needed to resolve the horizon and flatness problems. The potential must have a minimum where the field can settle and inflation can end, converting the inflationary energy into the hot plasma of the early universe through a process called reheating. The reheating process must be efficient enough to thermalize the universe rapidly and produce the hot dense state from which standard Big Bang evolution proceeds. Reheating is itself an important and incompletely understood part of the inflationary story. When the inflaton field reaches the minimum of its potential, it oscillates. These oscillations can transfer energy to other fields through various coupling mechanisms, producing particles and thermalizing them into the hot plasma. The details of reheating determine the reheat temperature, the temperature at which the universe becomes thermal after inflation, and this temperature is not directly observable. It affects the subsequent evolution in ways that can in principle be inferred, but it adds another layer of uncertainty to the inflationary story. The inflaton must also have the right initial conditions for inflation to begin. This is a subtle issue that is often glossed over. For inflation to solve the initial conditions problems of the hot Big Bang, it must itself start from initial conditions that are in some sense less finely tuned than those it is solving. If inflation requires initial conditions that are just as special as the conditions it is explaining, then it has not actually provided an explanation, but only moved the problem to an earlier time. This issue is most acute in the question of whether inflation begins generically or requires special conditions. Some analyses suggest that the onset of inflation is highly probable given a wide range of initial conditions for the inflaton field, while others suggest that the field must be carefully arranged to be in a slow-roll configuration initially. The debate is not resolved, and it depends on how one defines probability over initial conditions for a cosmological system, a question that is itself deeply problematic because we have only one universe to observe. One response to this concern is that even if inflation requires some initial fine-tuning, it still provides a net simplification. Instead of fine-tuning the entire early universe to be smooth, flat, and filled with specific fluctuations, you fine-tune only the initial state of the inflaton field, which is a simpler object. The fine-tuning is concentrated in one place rather than spread across the entire cosmological initial condition. This may not be philosophically satisfying as a complete explanation, but it may be a step toward one. Another response comes from eternal inflation, the idea that once inflation begins in any region, it tends to produce a fractal structure of inflating and non-inflating regions, with inflation ending in some parts while continuing in others. In the eternal inflation picture, the universe is not a single episode of inflation followed by a hot Big Bang, but a vast, possibly infinite, patchwork of regions in different stages of inflation and post-inflationary evolution. Our observable universe is just one small pocket that has exited inflation and thermalized. The question of initial conditions is then displaced onto the question of what started the eternal inflation process, which has its own initial conditions problem. We will return to eternal inflation in the chapter on the multiverse, because it has profound implications for the nature of physical law, for the meaning of explanation in cosmology, and for the possibility of testing cosmological theories. For now, the key point is that inflation, in its basic form, is a powerful framework that explains several features of the early universe that the hot Big Bang leaves unexplained, and it makes specific predictions that have been confirmed by observations. But it is not a complete theory of the beginning. It explains what happened a fraction of a second before the hot dense phase by invoking a dynamical process, but it does not explain where the inflaton came from, why it had the right potential, or what set its initial conditions. The transition from inflation to the hot Big Bang, the process of reheating, is worth examining in some detail because it illustrates how much of the inflationary story remains to be filled in. The universe during inflation is cold and nearly empty in the ordinary matter sense. The dominant energy is in the inflaton field, not in a hot plasma of particles. For the universe to transition into the hot dense state described by Big Bang cosmology, the inflationary energy must be converted into ordinary particles and thermalized. The conversion happens as the inflaton field decays, producing other particles through whatever couplings exist between the inflaton and the standard model fields. The details of this process depend on the inflaton's couplings, which are not constrained by the CMB observations of the perturbation spectrum. They depend on parameters that are essentially free within most inflationary models. In the simplest scenarios, the inflaton oscillates around the minimum of its potential after inflation ends, and these oscillations decay perturbatively into other particles through gravitational or direct couplings. The rate of decay depends on the coupling strengths, and the decay produces a thermalized plasma at a reheating temperature that can range from very high, close to the inflationary energy scale, to quite low, depending on the coupling strength. In more sophisticated scenarios, the decay can proceed through parametric resonance, a process called preheating, where the oscillating inflaton field drives exponential particle production through a resonance effect. Preheating can transfer energy very efficiently and rapidly, creating far from equilibrium distributions of particles that subsequently thermalize through scattering. The details of preheating and its transition to full thermalization are an active area of research using lattice field theory simulations. The reheating temperature matters for subsequent cosmological evolution. If it is above the electroweak scale, baryogenesis can proceed through electroweak mechanisms. If it is above the gut scale, heavy particles produced during reheating can decay asymmetrically and generate the baryon asymmetry through leptogenesis or direct baryogenesis. If it is too low, the baryon asymmetry and dark matter density must be generated through low-temperature mechanisms. The baryon asymmetry, the excessive matter over antimatter that filled the universe with atoms, is one of the great unsolved problems of cosmology and particle physics jointly. We know the asymmetry exists. Every atom we have ever measured or detected is made of matter, not antimatter. We know its size, roughly 1 baryon for every 10 billion photons in the universe today, or equivalently, a baryon-to-photon ratio of roughly 6 times 10 to the minus 10. This small number, determined independently by BBN and by the CMB, represents the fractional excessive matter over antimatter in the early universe, after which the remaining matter and antimatter annihilated into photons. Generating this asymmetry from symmetric initial conditions requires the three Sakharov conditions: violation of baryon number, violation of charge and charge parity symmetries, C and CP, and departure from thermal equilibrium. The Standard Model satisfies all three conditions in principle. Baryon number is violated by Sphaleron processes at the electroweak scale, CP is violated in the quark sector through the CKM matrix, and the electroweak transition provides departure from equilibrium. But as we noted, the Standard Model's CP violation is too small, and the electroweak transition too gentle for these mechanisms to generate the observed asymmetry. New physics is required. The search for additional sources of CP violation and for more dramatic departures from equilibrium in the early universe is therefore an active frontier connecting particle physics to cosmology. Various proposals invoke heavy sterile neutrinos whose CP violating decays generate a lepton asymmetry that is later partially converted to a baryon asymmetry by Sphaleron processes, a mechanism called leptogenesis. Others invoke extended Higgs sectors that make the electroweak transition more violent. Others look to the gut scale for baryon-violating processes with sufficient CP violation. Whatever the mechanism, baryogenesis must have occurred, and its scale connects the inflationary epoch to the subsequent hot Big Bang evolution. The reheating temperature determines which mechanisms were available, and the observed baryon-to-photon ratio provides a precise target that any successful mechanism must hit. This is one of the places where the story of the beginning becomes most concretely connected to physics that can be tested in particle accelerators, even if the full resolution may require energies beyond current reach. We have traced the timeline backward through the QCD epoch, through the electroweak transition, through the regime of grand unification and inflation, toward the Planck epoch where classical descriptions must give way to quantum gravity. At each step, the physics has become less tested and the uncertainties have grown, but the connection to observations has remained. The CMB, BBN, and large-scale structure constrain the early universe at the level of minutes and hundreds of thousands of years. The spectral index and B-mode limits constrain the inflationary mechanism at the energy scale where it operated. The baryon asymmetry constrains the processes that occurred between inflation and nucleosynthesis. What lies at the Planck epoch itself, and what preceded it if before is a meaningful concept there, is the deepest question. The Planck epoch is not merely an era of extreme temperatures. It is a domain where the very framework of physics as we understand it breaks down. General relativity, our description of gravity and spacetime, and quantum field theory, our description of particles and other forces, are not yet reconciled into a single framework. At the Planck scale, both must be relevant simultaneously, and their incompatibility forces us to acknowledge that our current theoretical toolbox is insufficient. This acknowledgement is not a failure. It is a precise localization of where new understanding is needed. We know approximately where the map ends. We can identify the features of the territory that the new map must reproduce, and we have several serious proposals for what the new map might look like. None of these proposals is established, but they are not guesses either. They are serious attempts to extend physics into a domain where current theories fail, guided by mathematical consistency, physical intuition, and indirect observational constraints. In the next part, we will examine the most serious of these proposals: inflation in greater depth, bounce cosmologies that replace the singularity with a transition from a prior phase, the Hartle-Hawking no-boundary proposal and its competitors, the role of the quantum vacuum in theories of the beginning, and the profound questions about the nature of time and causality that arise when spacetime is itself part of what must be explained. We will keep the observational constraints in view throughout, because the most powerful thing about this investigation is that it is not purely philosophical. The universe leaves clues, not just to its present state, but to its deepest past. our instruments are becoming sensitive enough to read those clues with increasing precision. And the answers, when they come, will come from a combination of theoretical insight and observational discipline, each checking the other, neither sufficient alone. The journey to the beginning is not over. In important ways, it has barely begun. The inflationary proposal sits at an interesting position in the landscape of scientific ideas. It is not a single theory but a framework, a class of models sharing the same basic mechanism of early accelerated expansion, differing in their details, their motivations, and their predictions. This flexibility is both a strength and a weakness. The strength is that the framework is robust. Many different implementations of the basic idea produce the same qualitative outcomes, resolving the horizon and flatness problems and generating a nearly scale-invariant spectrum of perturbations. The weakness is that this same flexibility makes inflation difficult to falsify as a general framework, because even when specific models are ruled out, others can be constructed to replace them. Understanding this tension is essential for evaluating what inflation actually tells us about the beginning of the universe. Inflation earns genuine empirical support from the CMB measurements. But the support is for the general framework, not for any specific model, and certainly not for a specific identification of the inflated field or a specific derivation of its potential from fundamental physics. The inflationary mechanism is constrained but not fully specified by current data. And the question of what drove inflation, what the inflaton actually is and where it came from, is open in a way that connects directly to the question of what caused the Big Bang. To see why, consider what inflation requires in terms of initial conditions. The universe must have contained a region, possibly very small, where the inflaton field was displaced from the minimum of its potential and in a configuration suitable for slow roll. The field must have been sufficiently uniform over that region, its energy density dominated by potential rather than kinetic energy, and the region must have been free of large inhomogeneities that would disrupt the exponential expansion before it could smooth things out. These requirements are not trivially satisfied. They represent conditions on the state of the universe at the onset of inflation, and those conditions are themselves in need of explanation. We have exchanged the initial conditions problem of the hot Big Bang for an initial conditions problem of inflation. The inflation problem may be simpler in some sense, involving fewer degrees of freedom or less extreme fine-tuning, but it is not absent. Different researchers assess this trade in different ways. Some argue that the conditions for inflation are natural in the sense that they occupy a large fraction of the space of possible initial states when measured in an appropriate way. Others argue that the measure problem, the question of how to assign probabilities to initial conditions for a cosmological system, is so poorly understood that no honest probability statement can be made. The measure problem is genuinely difficult, not merely technically complicated but conceptually unclear, because there is no obvious physical procedure for counting universes or sampling from the space of initial conditions. This difficulty points toward a deeper issue. To explain inflation's initial conditions, we need a theory of what determined those conditions. And that theory operates at the Planck epoch or earlier, in a regime where quantum gravity is essential and where time itself may not yet be a well-defined concept. Inflation as a mechanism sits between the Planck epoch and the hot Big Bang, explaining one in terms of the other, but leaving both boundaries open. The Planck epoch remains the deep mystery that inflation does not reach. Eternal inflation is the scenario that arises when inflation, once started somewhere, tends to continue indefinitely in other regions even as it ends locally. It follows from a simple observation about the dynamics of a scalar field in a landscape of possible potential values. If the inflaton field can take on a range of values, and if the potential has a sufficiently broad plateau or series of local minima, then quantum fluctuations during inflation can push the field uphill as often as the classical slow roll pushes it downhill. In regions where quantum fluctuations win, inflation continues. In regions where the classical roll wins, inflation ends and a hot Big Bang occurs. The result is a self-reproducing structure. Any region of inflating space generates more inflating space faster than it generates non-inflating regions. The total volume of inflating space grows without bound, even as local regions exit inflation and become hot Big Bangs. Inflation, once started, does not end globally. It continues forever in an ever-expanding frontier, producing an infinite number of post-inflationary regions, each potentially with different physical properties depending on which local minimum of the potential the field settles into. This scenario was developed in detail by Andre Linde and others in the 1980s and 1990s, and it has profound implications for the question of origins. If eternal inflation is correct, then our observable universe is not the universe. It is one pocket in an infinite patchwork of post-inflationary regions, each with its own reheating history, its own particle physics in principle, and its own cosmological evolution. The Big Bang that began our observable universe is one of infinitely many such events, all occurring within the larger eternally inflating spacetime. In this picture, asking what caused the Big Bang is like asking what caused a particular water droplet in an infinite ocean. It had local causes within the larger structure, but the larger structure itself may have no beginning in the ordinary sense. Eternal inflation does not eliminate the problem of origins, it moves it. Instead of asking what caused a single Big Bang, we ask what caused the eternal inflation process to begin, and what determined the structure of the potential landscape that inflation explores. These questions are just as deep as the original one, but they are different questions. They point toward a theory of the inflationary landscape, which connects to string theory's landscape of possible vacuum states, and toward the initial conditions of eternal inflation itself. The string theory landscape deserves careful examination because it has become one of the most discussed and most contested ideas in fundamental physics. String theory, as we noted earlier, does not predict a unique low-energy physics. The different ways of compactifying the extra dimensions of string theory into our four-dimensional spacetime produce different effective theories with different particle contents, different force strengths, and different vacuum energies. The number of distinct compactifications, and therefore the number of different effective theories, is estimated to be enormous, often quoted as 10 to the 500th power or more, though the precise count is uncertain and the enumeration is not complete. Each of these effective theories corresponds to a different vacuum state of the landscape, a different local minimum of a potential in some high-dimensional space of parameters. Eternal inflation can explore this landscape by producing different post-inflationary regions that settle into different vacuum states. If the landscape is as vast as estimated, and if eternal inflation explores it, then our observable universe is one sample from an enormous ensemble of possible universes, each with potentially different physical laws. This is a profound and genuinely radical idea, but it comes with severe problems for scientific epistemology. If there are infinitely many universes with different physical laws, and if observers can only exist in universes where the laws are compatible with complex structures in biology, then the observed properties of our universe are partially explained by this selection effect, the anthropic principle, without being uniquely predicted. The specific values of physical constants, which appear fine-tuned for life in ways that have long puzzled physicists, would simply be the values that happen to exist in one of the many universes that are hospitable to observers. We find ourselves in such a universe because only such universes contain observers who can ask about their properties. The anthropic reasoning is not logically flawed, but it is scientifically troubling because it can explain almost anything after the fact and predict almost nothing in advance. If the landscape is sufficiently diverse and eternal inflation explores it sufficiently thoroughly, then essentially any set of physical laws is realized somewhere, and the question becomes why the laws in our region are what they are becomes partially a question about the abundance of different types of universes weighted by their ability to produce observers. This anthropic weighting is called the measure problem in the context of the landscape, and it is not solved. Without a well-defined measure, the landscape makes no definite predictions. Some physicists find this unsatisfying to the point of considering it outside science. If a theory cannot make definite predictions, it cannot be tested, and a theory that cannot be tested is not a scientific theory in the standard sense. This critique has been made forcefully by critics of the landscape, including physicists who are otherwise sympathetic to string theory, and it has not been fully answered. The defenders of the landscape argue that it is an honest response to the observed fine-tuning of constants, that the alternative of requiring a unique prediction from fundamental theory may be too strict a criterion, and that even statistical predictions from the landscape may eventually be testable as our understanding of the measure improves. The debate is live and unresolved, and its resolution matters enormously for the question of origins. If the landscape is real and eternal inflation explores it, then the question of why our universe has the properties it has may have an anthropic answer, supplemented by a measure-weighted statistical statement. That is a very different kind of answer from a dynamical explanation, and many physicists find it deeply unsatisfying, even if they cannot immediately refute it. Stepping back from the landscape and returning to more concrete territory, we can examine what happens when you take seriously the possibility that the singularity can be avoided, that the beginning of our universe is not a mathematical divergence, but a physical transition from a prior state. This is the idea behind bouncing cosmologies, a broad class of models that replace the Big Bang singularity with a bounce, a moment of minimum size and maximum density from which the universe expands after having previously contracted. The simplest version of a bouncing cosmology imagines the universe cycling through phases of expansion and contraction, bouncing at each minimum. This cyclic model has a long history, predating modern cosmology, and the intuitive appeal is obvious. A universe that oscillates eternally avoids the question of a beginning by having no beginning at all. The universe has always existed, alternating between expanding and contracting phases. The difficulty with the classical cyclic model is entropy. Each bounce preserves and typically increases the entropy of the universe, as required by the second law of thermodynamics. Over many cycles, the entropy accumulates, and the universe would grow larger and hotter with each cycle, making it impossible to trace back to an infinite past of identical cycles. The second law does not allow a perfect repeating cycle. It allows a cycle that changes with each iteration, and the changes accumulate in a way that points toward a beginning even in a cyclic model, merely displacing the problem rather than eliminating it. Modern bouncing cosmologies address this differently. Rather than cyclic classical evolution, they invoke quantum effects or modifications of gravity that prevent the singularity from forming and replace it with a smooth transition. The most mathematically developed of these is loop quantum cosmology. Loop quantum cosmology applies the quantization techniques of loop quantum gravity to the cosmological setting, replacing the smooth, continuous geometry of classical cosmology with a discrete quantum geometry. In this framework, the scale factor of the universe is not a classical continuous variable, but a quantum observable, and its spectrum is discrete at the Planck scale. The quantum geometry produces effective modifications to the Friedmann equations that change how the universe behaves near the Planck density. In the classical Friedmann equations, the energy density appears in a term that drives expansion. As you increase the density, you get faster expansion, and running backward in time, the density diverges at the singularity. In loop quantum cosmology, there is a quantum correction that becomes significant near the Planck density. This correction introduces a term with the opposite sign, which becomes increasingly important as density rises, and eventually exactly cancels the classical term at a critical density equal to roughly the Planck density. Above this critical density, the quantum correction dominates, and the effective equation of state changes so that the universe bounces rather than collapses to a singularity. The bounce in loop quantum cosmology is not a dramatic event in the classical sense. It is a transition through a quantum regime, a phase where the classical description of spacetime breaks down and the quantum geometry takes over. On both sides of the bounce, the classical description of an expanding or contracting Friedmann universe is recovered. In between, the quantum geometry provides a smooth connection that replaces the classical singularity. This resolves the singularity technically, but it raises new questions. What was the pre-bounce universe like? If the universe contracted to Planck density and then bounced, what were the conditions during the contracting phase? Were they similar to those of the expanding phase or radically different? Did the pre-bounce universe contain structure? And if so, does that structure get transmitted through the bounce to influence the post-bounce universe? These questions have been studied in loop quantum cosmology, and the results are partially encouraging and partially unsettled. Some studies suggest that the bounce can transmit certain types of perturbations from the pre-bounce phase to the post-bounce phase, leaving imprints that could in principle be detected in the CMB. Others suggest that the quantum regime near the bounce scrambles information so thoroughly that the post-bounce state is essentially independent of the pre-bounce state, making it impossible to learn about the pre-bounce universe from observations. The verdict depends on technical details of the quantization procedure and on the interpretation of the quantum state near the bounce. One interesting aspect of loop quantum cosmology's prediction is that it modifies the dispersion relation of primordial perturbations in ways that could leave observable imprints on the CMB power spectrum at the largest angular scales. Modes that were stretched to scales larger than the Planck length during the bounce would carry quantum gravity corrections that might show up as slight departures from the standard inflation plus expansion prediction at the largest angular scales, where the CMB already shows some anomalies that may or may not be physically significant. The CMB anomalies at large angular scales, including a low power in the quadrupole, an alignment of low multipoles, and a hemispherical asymmetry in power, have been noted since the WMAP era and confirmed by Planck. Their statistical significance is debated, and they may be the result of cosmic variance, the fundamental limit on statistical precision from having only one sky to measure. But they are also predicted by some quantum gravity corrections, and the possibility that they reflect genuine physics from the Planck era is tantalizing even if not established. A different approach to the bouncing cosmology is the ekpyrotic scenario, proposed by Paul Steinhardt, Neil Turok, and collaborators. The ekpyrotic scenario is motivated by string theory and M-theory, specifically by the idea that our observable universe is a three-dimensional membrane, a brain moving through a higher dimensional space. In the original ekpyrotic model, our brain collides with a neighboring brain, and the collision releases energy that produces the hot Big Bang. The bounce is not a collapse and re-expansion of a single universe, but a collision between brains in a higher dimensional space. The ekpyrotic scenario makes specific predictions for the primordial perturbation spectrum that differ from simple inflationary models. In particular, the spectrum of gravitational waves produced in the ekpyrotic scenario is steeply blue-tilted, meaning gravitational waves at shorter wavelengths are much stronger than at longer wavelengths. This is the opposite of the nearly scale-invariant or red-tilted spectrum predicted by most inflationary models. If the primordial gravitational wave background is ever detected, its spectral shape would immediately distinguish between the ekpyrotic scenario and inflation. The cyclic version of the ekpyrotic scenario, developed by Steinhardt and Turok, proposes that the brain collision happens repeatedly, with each cycle producing a new Big Bang. In this picture, the universe has no beginning in the ordinary sense, but has been cycling through expansions and contractions for an indefinitely long past. The entropy problem is addressed differently than in the classical cyclic model. In the cyclic ekpyrotic scenario, the universe grows by an exponential factor in each cycle, so the entropy density dilutes even as the total entropy increases, effectively resetting the conditions for structure formation in each new cycle. The cyclic ekpyrotic scenario is mathematically sophisticated and genuinely different from inflationary cosmology in its predictions, but it faces its own challenges. The collision of brains through a higher dimensional space is difficult to model reliably, and the behavior of perturbations through the bounce, specifically how quantum fluctuations in the pre-collision phase become the density perturbations we observe in the CMB, is not fully worked out and depends on assumptions about what happens at the singular collision point. The pre-Big Bang scenario proposed by Gasparini and Veneziano in the context of string theory is another approach. In this scenario, the universe began in a different phase described by the dilatant field of string theory, a field that controls the overall strength of string interactions. The pre-Big Bang phase is a low-curvature, weakly coupled expanding phase that undergoes a transition to a high-curvature phase, which then matches onto the standard Big Bang. The transition requires a mechanism to connect the two phases, and as in the ekpyrotic case, the behavior of perturbations through the transition is technically challenging. What these various bouncing and cyclic models share is the attempt to replace the singularity with a physical transition, to avoid the need for an absolute beginning by embedding our Big Bang in a larger temporal context. They differ in their motivations, their mathematical frameworks, their specific predictions, and their degree of development. None of them is as well developed or as well connected to observational evidence as inflationary cosmology, but they represent genuine alternatives that make different predictions and could be distinguished by future observations, particularly measurements of the primordial gravitational wave background. There is another class of proposals for the beginning of the universe that takes a radically different approach, one that does not try to extend the universe's history to an earlier time, but instead tries to show that the universe can arise from nothing, or from a state that is as close to nothing as physically meaningful. These proposals are associated with the names Hartle and Hawking, Vilenkin and Lind, and they each represent a different take on what it means for a universe to be. Stephen Hawking and James Hartle proposed in 1983 what they called the no-boundary proposal, or the no-boundary wave function of the universe. The proposal is formulated in the language of quantum cosmology, which applies quantum mechanics not just to the matter content of the universe, but to the geometry of spacetime itself. In quantum mechanics, a particle does not have a definite trajectory, but rather a wave function that gives the probability amplitude for different configurations. In quantum cosmology, the universe has a wave function that gives the probability amplitude for different geometries and matter configurations. The Hartle-Hawking proposal specifies a particular choice of quantum state for the universe, one defined by summing over all compact four-dimensional geometries without boundary, weighted by the exponential of minus the Euclidean action. The key feature is the no-boundary condition itself. The four-dimensional geometry is smooth and compact, without any boundary in the past. This is achieved by a mathematical technique called Wick rotation, which replaces time with imaginary time, turning the Lorentzian spacetime of ordinary physics into a Euclidean geometry, where there is no distinguished time direction. In the Euclidean geometry, the universe is like a sphere. A sphere has no edge and no boundary. You can move anywhere on its surface without reaching a point where you fall off. In this picture, asking what happened before the Big Bang is like asking what is south of the South Pole. The question assumes there is a boundary to cross, but the no-boundary condition says there is no boundary. Time, as we normally experience it, emerges from the Lorentzian geometry that describes the universe after the Euclidean phase, and it has no analog in the Euclidean phase itself. This is a mathematically precise and conceptually striking proposal, but it has been the subject of significant debate since it was first proposed. One central issue is the path integral over geometries itself, which is not rigorously defined in the Lorentzian case and requires the Euclidean rotation to make mathematical sense. But the Euclidean geometry does not have a direct physical interpretation in the same way that the Lorentzian spacetime does, and the physical meaning of summing over Euclidean geometries is not entirely clear. A more recent set of concerns has been raised by calculations examining the quantum fluctuations predicted by the no-boundary state. Neil Tirach, Jonathan Halliwell, and others have found that in some formulations, the no-boundary state predicts a universe that is unstable or dominated by large fluctuations rather than the smooth, nearly homogeneous universe we observe. The debate about whether these calculations correctly implement the no-boundary proposal and whether they undermine or merely constrain it is ongoing and technical, involving subtleties about which contours to use in the path integral and how to interpret the results physically. The Hartle-Hawking proposal has also been criticized on philosophical grounds for appearing to derive the universe from nothing while actually assuming the existence of mathematical structures, Euclidean geometries, path integrals, and physical laws that are themselves something rather than nothing. This objection applies to most physical proposals for the origin of the universe. Any theory that invokes quantum mechanics, or fields, or mathematical laws is starting from something, not from genuine nothingness. The question of why there are mathematical laws at all is not answered by any of these proposals. Alexander Vilenkin proposed an alternative quantum cosmological model in the early 1980s, in which the universe tunnels from literally nothing, a state with no spacetime at all, to a finite-sized de Sitter universe through a process called quantum tunneling from nothing. In quantum mechanics, particles can tunnel through energy barriers that they would not be able to cross classically, appearing on the other side of the barrier with some probability. Vilenkin's proposal applies this idea to the geometry of spacetime itself, proposing that a spacetime with no spatial extent can quantum mechanically tunnel to a small finite-sized spacetime, which then undergoes inflationary expansion. This is an extraordinary claim, and it requires careful examination. Quantum tunneling in ordinary physics occurs within a pre-existing quantum mechanical framework, with a pre-existing Hilbert space, a pre-existing Hamiltonian, and a pre-existing time variable. The tunneling happens within a context that is already there. Vilenkin's tunneling from nothing must somehow involve a quantum process that creates the very framework in which quantum processes occur. This is not an ordinary tunneling event, but a bootstrap, a self-creating structure that has no pre-existing context. The mathematical implementation of this idea uses the same path integral machinery as the Hartle-Hawking proposal, but with a different boundary condition. Rather than summing over compact geometries with no boundary, Vilenkin sums over geometries with a specific boundary condition at the initial state that represents nothing. The two proposals make different predictions for the probability of different initial states, and therefore for the observable properties of the universe, providing in principle a way to distinguish them empirically. André Linde proposed a related scenario called chaotic inflation, which has an eternal character that connects it to the eternal inflation discussed earlier. In Linde's chaotic inflation, the universe does not need to begin in any specific state. Given a sufficiently broad potential for the inflated field, quantum fluctuations can continuously generate patches of the universe in different field configurations, including configurations that support inflation. The universe is self-sustaining in the sense that the inflating regions produce more inflating regions faster than they produce non-inflating ones, and the process continues indefinitely both into the future, and in some formulations, also into the past. These proposals share the feature of trying to make the universe's beginning as natural or as automatic as possible, to reduce the apparent fine-tuning of initial conditions by showing that the universe we observe would arise naturally, or with high probability, from the simplest possible starting point. The starting point differs between proposals, and the degree to which they succeed is debated, but they represent serious attempts to grapple with the beginning question using the tools of quantum mechanics and field theory, and they make predictions that can in principle be tested. the nature of the quantum state of the universe, is a genuinely difficult concept, and it is worth pausing to understand why, because the difficulty illuminates the deepest aspects of the origins problem. In ordinary quantum mechanics, a particle has a wave function that evolves in time according to the Schrödinger equation. The wave function gives the probability amplitude for different measurement outcomes, and the evolution is deterministic in the sense that given the wave function at one time, you can compute it at all other times. But the wave function is defined in time, it evolves in time, and it requires a background time coordinate to be interpreted. In quantum cosmology, the universe as a whole has a wave function, but there is no background time external to the universe against which the wave function can evolve. The universe is everything, and time is part of the universe. The wave function of the universe satisfies not the Schrödinger equation, but the Wheeler-de Witt equation, which is a constraint equation with no explicit time dependence. The wave function is defined on the space of three-dimensional geometries and matter configurations, called superspace, and the Wheeler-de Witt equation tells you which wave functions are physically allowed, but it does not tell you how they evolve in time. Time, in the quantum cosmological context, must be extracted from the wave function itself, rather than being given from outside. This is the problem of time in quantum gravity, and it is one of the deepest conceptual difficulties in the field. Various proposals exist for how to recover an effective time evolution from the timeless Wheeler-de Witt equation. One approach uses correlations between different parts of the universe, defining time operationally as the value of a particular degree of freedom, like the scale factor or some matter field, against which other degrees of freedom are correlated. Time is then not a background parameter but an internal relational quantity, defined by relationships between subsystems. This relational view of time has profound implications for causality. If time is relational and emergent rather than fundamental, then causal relationships, which are defined within time, are also emergent. At the fundamental level described by the Wheeler-de Witt equation, there is no time, no causality, and no evolution in the ordinary sense. There is only a timeless wave function on superspace. The apparent flow of time, the sequence of events, the causal structure of the universe, all emerge from the entanglement structure of the wave function and from the way we as observers are embedded within the universe. This is a radically different picture from the everyday understanding of time and causality, and it changes what it means to ask what caused the Big Bang. If time is emergent, then the question assumes a temporal framework that does not exist at the fundamental level. Asking for a cause of the Big Bang in a theory where time is emergent is asking for a causal relationship in a domain where causality is not a fundamental concept. The question may need to be replaced by a different kind of question, one that can be asked within the timeless framework of quantum gravity. What would such a question look like? One possibility is to ask for the wave function of the universe rather than for a cause. The wave function specifies the probability amplitude for all possible configurations of the universe, including configurations that look like a hot Big Bang at some effective time. If the wave function is determined by a principle, like the Hartle-Hawking no-boundary condition or the Vilenkin tunneling wave function, then that principle explains the universe without invoking a temporal cause. The explanation is structural rather than causal. The universe is this way because the wave function has these properties, not because something earlier made it so. This is genuinely unsatisfying to the part of our brain that insists on narrative and temporal sequence. But the universe is not obligated to organize itself around our intuitions, and the most important disciplines of physics have repeatedly required us to revise those intuitions when the evidence demands it. Special relativity required revising intuitions about simultaneity and the universality of time. Quantum mechanics required revising intuitions about determinism and the definiteness of properties before measurement. Quantum gravity may require revising intuitions about time itself as a fundamental feature of reality. The relationship between quantum mechanics and cosmological origins brings us to a topic that deserves careful treatment: the quantum vacuum and what it does and does not offer as an explanation for the universe's existence. In quantum field theory, the vacuum is not empty in the naive sense. It is the lowest energy state of a quantum field, but that state is not featureless. Quantum fields have zero-point fluctuations, temporary departures from their expectation values that are required by the uncertainty principle. These fluctuations do not correspond to real particles in the usual sense, but they have measurable consequences. The Casimir effect, the attraction between two closely spaced metal plates in vacuum, is one such consequence. The Lamb shift in atomic energy levels is another. The vacuum is a structured, dynamically active state, not a featureless absence. It is sometimes claimed that the universe arose from quantum vacuum fluctuations, and this claim is sometimes taken to imply that the universe came from nothing. The implication is deeply misleading. The quantum vacuum is very much a something. It is a state of a quantum field, which presupposes the existence of quantum fields and the mathematical framework of quantum field theory, including a Hilbert space, an algebra of operators, and a Hamiltonian. It also presupposes the existence of the background spacetime in which the fields are defined, unless you are working in a framework where spacetime is itself quantized, in which case you presuppose the quantum gravity framework. A quantum vacuum fluctuation that produces a universe would be a fluctuation not of ordinary quantum fields in flat spacetime, but of quantum gravitational degrees of freedom, of the wave function of the universe in superspace. This is a very different thing from an ordinary vacuum fluctuation, and it requires the entire quantum gravity framework as its context. The universe would be arising from a particular quantum state of a particular mathematical framework, not from literal nothingness. This does not mean the quantum cosmological proposals are wrong. It means they should be understood for what they are: attempts to explain the universe's beginning within a quantum mechanical framework that is itself not derived from more basic principles. The framework is assumed, and the universe arises within it. The question of why this framework rather than some other, or rather than no framework at all, is not answered by any of these proposals. The philosopher David Albert has made this point forcefully in response to Lawrence Krauss's book, arguing that the universe came from nothing. Albert's critique is that the nothing Krauss invokes is actually a something, specifically a relativistic quantum field theory in its vacuum state, and that this is not the philosophical nothing that the question of origins is asking about. Albert's point is not pedantic. It highlights a genuine gap between the physical proposals and the philosophical question, a gap that cannot be closed by any physical theory alone, because the gap is about why physical theories exist at all. This does not mean the question of cosmological origins is outside science. It means the question has both a scientific dimension, which physical process or principle accounts for the observable properties of the early universe, and a philosophical dimension, why does anything exist rather than nothing? And these two dimensions are not the same question, even though they are often conflated. Scientific cosmology can make progress on the first dimension without necessarily resolving the second. And conflating them produces confusion in both directions, making the science seem more conclusive than it is on the philosophical question, and making the philosophical difficulty seem like a reason to dismiss the scientific progress. The question of nothing and something is not merely verbal. It has a technical dimension in physics that is worth exploring carefully, because modern physics has genuinely changed what we mean when we say empty space. In classical physics, empty space is genuinely empty. It is a static background arena in which things happen, with no properties of its own beyond its geometry. In special relativity, empty space has a geometry but no dynamics. In general relativity, space has a geometry that responds to the presence of matter and energy, so empty space in the presence of matter is curved, but empty space in the absence of matter is flat and featureless. In quantum field theory, empty space becomes dynamically rich. Every quantum field has a ground state, and the ground state energy of a field is not zero. It is the zero-point energy, the minimum energy required by the uncertainty principle, even when no excitations are present. The vacuum is filled with these zero-point fluctuations, and it has a definite energy density, the vacuum energy, that persists even in the absence of any particles. Furthermore, the vacuum can undergo transitions. A field in a local minimum of its potential is in a metastable vacuum state. If a lower energy vacuum exists, the field can quantum mechanically tunnel to the lower energy state, a process called vacuum decay. This is not a metaphor. It is a precise prediction of quantum field theory with specific calculable rates. If our current vacuum is metastable, it might eventually decay to a lower energy state, and the resulting bubble of new vacuum would expand at the speed of light, altering the physical laws within its interior. The possibility of vacuum decay connects to the landscape of string theory, where different vacuum states correspond to different local minima of a high-dimensional potential. Eternal inflation can drive transitions between these vacuum states by quantum tunneling, populating different regions of the landscape in different post-inflationary pockets. Our own universe may be one such pocket, settled into a particular vacuum state with the particle physics and constants we observe. The nature of our vacuum, including its stability, its dark energy density, and the masses and couplings of its particles, would then be determined by which local minimum we happen to settle into after inflation. The vacuum energy of our universe, as measured from the observed cosmological constant, is extraordinarily small, roughly 10 to the minus 123 in Planck units. This number is astonishing because naive calculations of the quantum vacuum energy give numbers many orders of magnitude larger. The discrepancy, sometimes called the cosmological constant problem, is the worst fine-tuning problem in physics. Something is causing the contributions from quantum fields to the vacuum energy to cancel almost perfectly, leaving the tiny observed remnant. No one knows what causes this near-perfect cancellation. In the landscape context, the observed small value of the vacuum energy could be explained anthropically. Universes with large vacuum energies either expand too fast for structure to form or recollapse too quickly. Only universes with very small vacuum energies can host galaxies, stars, and observers. If the landscape populates all possible values of the vacuum energy, and if observers can only arise in a narrow range, then we should expect to find ourselves in a universe with a small cosmological constant, even if most regions of the landscape have large values. This anthropic explanation of the cosmological constant was proposed by Weinberg before the observational discovery of dark energy, and the subsequent confirmation that the cosmological constant is small but non-zero has been seen by some as a success of anthropic reasoning, and by others as an insufficient prediction. The vacuum structure of the theory is therefore deeply connected to the cosmological constant, to the stability of our universe, and to the question of what kind of beginning our pocket universe had. If we are in a landscape pocket that tunneled from another vacuum state, our beginning was not the Planck-epoch Big Bang singularity in the classical sense, but a quantum tunneling event from a de Sitter or other inflating background. The singularity would be replaced by a smooth tunneling transition, and the pre-tunneling state would be a different vacuum of the same theory. We have been exploring the boundaries of what physics can say about the beginning, and it is time to be explicit about where those boundaries lie and why they matter for the central question. The standard Big Bang model, with inflation, accounts for the observed properties of the universe with remarkable success. It explains the CMB, the light element abundances, the large-scale structure, and the primordial perturbation spectrum. The inflationary mechanism provides a dynamical explanation for the smoothness and flatness of the early universe and for the near-scale invariant perturbation spectrum. These are genuine achievements that constrain the history of the universe back to fractions of a second after the hot dense phase. But this framework does not explain what set the initial conditions for inflation. It does not explain the identity of the inflatoned field or the shape of its potential. It does not resolve the singularity or provide a description of the Planck epoch. It does not explain the baryon asymmetry from first principles. It does not identify dark matter or explain its density. It does not explain dark energy or account for the enormous fine-tuning of the cosmological constant. These are not minor gaps in an otherwise complete picture. They are central, open problems that connect to the deepest questions about the beginning. Each of them, if resolved, would transform our understanding of what the beginning was and why it had the properties it had. And each of them points in the same direction, toward physics beyond the standard model, beyond general relativity, and beyond the tested domain of current science. The proposals that exist for addressing these problems, quantum cosmological wave functions, bouncing cosmologies, the landscape and eternal inflation, string-theoretic brain-world scenarios, are serious scientific efforts that engage mathematically with the questions and make predictions that could in principle be tested. But none of them is established, and the observational constraints available to us, while impressive and growing, have not yet been sufficient to select among them. This is the current state of the art, a well-tested framework with open boundaries and a range of serious proposals for what lies beyond those boundaries, constrained but not yet selected by observations. The science is alive and productive, not stagnant, and the prospects for progress are real. Future CMB polarization measurements, galaxy surveys, gravitational wave detectors, and potentially direct dark matter detection could all provide new constraints that shift the balance among competing proposals. One of the most important constraints that future observations could provide is the measurement of the tensor-to-scalar ratio with sensitivity below the current limit of roughly 0.36. As noted earlier, the CMB-S4 experiment aims to reach sensitivity of order 0.1 or better, which would either detect primordial gravitational waves from inflation or set limits that rule out all large-field inflationary models. This measurement would significantly narrow the landscape of viable inflationary potentials and indirectly constrain the energy scale at which inflation occurred. If primordial gravitational waves are detected with a specific amplitude, the measurement of R would determine the inflationary energy scale to a precision that connects directly to particle physics models. At the Lith bound, There is a relationship between r and the distance the inflatoned field traveled in field space during inflation. A detectable value of r implies that the inflatoned traversed distances comparable to the Planck scale. This field-theoretic statement has implications for quantum gravity because super-Planckian field excursions are sensitive to corrections from Planck scale physics. A detection of r above roughly zero. One would therefore be a clue not just about inflation, but about quantum gravitational effects on scalar fields. If primordial gravitational waves are not detected even at the sensitivity of CMB-S4, the implications are also significant. All natural large-field inflationary models would be ruled out. The surviving models would be small-field models with plateau-like potentials, and the question of why the potential has that shape becomes more pressing. It would suggest that inflation operated at an energy scale well below the gut scale, changing the connection between inflation and grand unification. Beyond the CMB, the 21-centimeter line of neutral hydrogen offers a window into the cosmic dark ages between recombination and reionization, the period when the first stars lit up. This epoch is currently largely unobserved, but future radio telescopes like the Square Kilometre Array and its pathfinders will map the distribution of neutral hydrogen across this era with increasing sensitivity. The 21-centimeter signal carries information about the matter-power spectrum on small scales, about the first sources of ultraviolet radiation, and about any exotic physics that might have injected energy into the intergalactic medium during this period. Gravitational wave observatories offer another frontier. The ground-based detectors LIGO and Virgo have already detected gravitational waves from compact binary mergers, opening the era of gravitational wave astronomy. The space-based LISA detector, planned for launch in the 2030s, will be sensitive to lower-frequency gravitational waves, potentially including a stochastic background from the early universe. Such a background could arise from a first-order electroweak phase transition, from cosmic string networks produced by symmetry breaking, or from other violent early universe processes. Each source would have a characteristic spectrum that could identify the process and the energy scale at which it occurred. Pulsar timing arrays, which use precisely timed pulses from millisecond pulsars to detect the stretching and squeezing of spacetime caused by passing gravitational waves, have already found hints of a stochastic gravitational wave background at nanohertz frequencies. The source of this background is not yet identified. It may be from supermassive black hole binaries, or it may have a cosmological origin. As the data accumulate over the coming years and the sensitivity improves with more pulsars and longer time baselines, the spectral shape of the background may be measured well enough to distinguish between these options. A cosmological gravitational wave background at nanohertz frequencies would be evidence of processes occurring in the very early universe, possibly connected to phase transitions or other dynamics near the time of inflation or baryogenesis. Amid all of these observational possibilities and theoretical proposals, the deepest questions about the beginning remain open in a way that is philosophically significant rather than merely technically unresolved. The question of why there is something rather than nothing, in the strict philosophical sense, is not answerable by physics, because any physical answer will invoke some mathematical or physical structure whose own existence is not explained. The regress of explanation either terminates in an unexplained brute fact or produces a circular structure where the ultimate foundation justifies itself. This is not a failure of science. It is a recognition of the boundaries of the scientific method. Science is extraordinarily powerful for answering questions of the form. Given that a certain physical framework exists, what does it predict and how well do those predictions match observations? It is not designed, and perhaps not able, to answer the question of why any physical framework exists at all. The question of ultimate existence, why there is something rather than nothing in the deepest sense, is a philosophical question that has no purely scientific answer. What science can do, and what cosmology has done impressively, is push the question of why back further and further, explaining earlier states in terms of even earlier ones, replacing fine-tuned initial conditions with dynamical mechanisms, and identifying the specific points where new physics is required. This process does not end the philosophical question, but it changes its character. The universe we need to explain becomes progressively simpler as the dynamical mechanisms do more of the explanatory work. If inflation explains the smoothness of the CMB, and if a quantum cosmological wave function explains the conditions for inflation, and if that wave function is determined by a principle like the no-boundary condition, then the explanatory burden has been reduced to that principle itself. Why that principle and not another? At some level, this question may not have a deeper answer, but the question has been sharpened enormously. there is something important in the sharpening. The question of why the universe exists has been with us since human beings first began wondering about their circumstances. For most of history, it was addressed through mythology, theology, and philosophy. Modern physics has added a new dimension by identifying specific, quantitative constraints that any answer must satisfy. The universe is not just a philosophical puzzle. It is a measured, constrained, partially explained physical system, and the constraints it places on the nature of its own beginning are increasingly precise. That precision is itself a form of progress, even when it does not produce a complete answer. The fact that we can rule out certain types of beginnings, that we can say the early universe was not wildly chaotic, was not strongly curved, did not have a strongly non-Gaussian spectrum, was not dominated by cosmic strings or monopoles, all of this is genuine knowledge about the nature of the beginning. The universe is telling us, through its properties, what its beginning must have been like, even if it has not yet told us why. Let us consolidate what we have established in this part before moving forward, because the synthesis matters as much as the individual pieces. Inflation is a powerful framework that extends the hot Big Bang account of cosmic history by invoking a prior period of accelerated expansion. It explains the smoothness, flatness, and perturbation spectrum of the early universe through dynamics rather than fine-tuned initial conditions. It makes testable predictions that have been confirmed in their qualitative features and are being refined and tested in their quantitative details. But inflation does not explain what caused it, what the inflation is, or what happened at the Planck epoch before inflation began. Eternal inflation extends the inflationary picture into a vast, possibly infinite multiverse in which our observable universe is one pocket among many, potentially with different physical laws. It provides a context in which the conditions for inflation arise naturally and repeatedly. But it introduces the landscape problem and the measure problem, making definite predictions extraordinarily difficult and raising questions about whether the multiverse framework is scientifically testable in the standard sense. Bouncing cosmologies replace the singularity with a physical transition from a prior contracting phase, avoiding the need for an absolute beginning. Loop quantum cosmology provides a specific mathematical implementation of the bounce using the discrete quantum geometry of loop quantum gravity. Ekperiodic and cyclic models provide alternative implementations motivated by string theory and brane cosmology. All of these proposals face challenges in working out the behavior of perturbations through the bounce and in connecting pre-bounce physics to post-bounce observables. Quantum cosmological wave function proposals, including the Hartle-Hawking no-boundary proposal and the Vilenkin tunneling wave function, attempt to specify the initial state of the universe through a principle that does not invoke a prior classical state. They apply quantum mechanics to the geometry of spacetime itself and define the universe's beginning through a boundary condition in the space of geometries. These proposals are mathematically sophisticated but face deep interpretational difficulties related to the problem of time in quantum gravity and the definition of the path integral over geometries. All of these proposals share the feature of trying to push the explanation of the universe's beginning as deep as our physical understanding allows. None of them reaches the point of explaining why physical laws exist at all, or why there is something rather than nothing in the ultimate philosophical sense. This gap between physical explanation and philosophical grounding is not a failing of any specific proposal. It is a feature of the scientific enterprise itself, which can explain more and more in terms of less and less, but cannot explain everything in terms of nothing. The observational frontier is active and growing. Future measurements of CMB polarization, large-scale structure, gravitational waves, and the 21-centimeter background all offer opportunities to constrain the proposals and potentially select among them. The next decade will likely bring significant new data on the primordial gravitational wave background, on the small-scale matter power spectrum, and on the properties of the dark universe. These data may not resolve all of the deep questions, but they will narrow the space of viable answers and push the investigation forward. What remains constant throughout this exploration is the combination of humility and precision that defines good science at the frontier. The universe has shown us, repeatedly and emphatically, that our intuitions about the deep nature of things are not reliable guides. Time is not absolute. Space is not a fixed background. Matter is made of fields rather than solid particles. Gravity is the curvature of spacetime. Each of these revisions of intuition required accepting that the universe is stranger than it looks from our everyday vantage point. The nature of the beginning may require an equally profound revision, one in which time, causality, and the meaning of nothing are all understood differently from how we currently understand them. That revision has not yet been made in a form we all agree on. The proposals are on the table, the observations are accumulating, and the investigation is ongoing. The most honest and most scientifically accurate thing we can say is that we are making genuine progress on one of the hardest questions our species has ever asked, and the progress is real even though the answer is not complete. In the next part, we turn to the nature of time and causality more directly, asking what physics tells us about these concepts and how they might need to be revised when applied to the question of the universe's beginning. We will look at the arrow of time, the block universe interpretation of relativity, the emergence of time in quantum gravity, and what it means to ask for a cause when time itself is part of what must be explained. The answers are surprising, the questions are deep, and the journey from the comfortable familiar to the genuinely strange is perhaps the most important part of what the investigation of origins has to offer. Of all the concepts that the investigation of cosmic origins puts under pressure, time is the most fundamental and the most resistant to revision. We are saturated with time. Every experience we have is sequential. Every memory is ordered. Every plan we make assumes that causes precede effects, and that the future is open in a way the past is not. Time is so thoroughly woven into the fabric of conscious experience that questioning it feels less like doing physics and more like trying to see your own eyes directly. Questioning tool and the thing being questioned are the same instrument, and yet the investigation of the beginning forces exactly this questioning, not as a rhetorical move, not as philosophical decoration, but as a genuine physical necessity. When we push the history of the universe back to the Planck epoch, we reach a regime where the smooth, classical, directional time of everyday experience must give way to something else, something that our current theories can gesture toward but not fully describe. Understanding what time actually is, what its properties are, where it comes from, and what happens to it at the boundaries of the universe is not a detour from the central question. It is the central question dressed in its most fundamental clothes. We begin with the aspects of time that physics has already clarified, because they are already strange enough to disturb ordinary intuitions, and they prepare the ground for what the regime of quantum gravity demands. In Newtonian physics, time is absolute. It flows at the same rate everywhere, for everyone, regardless of motion or gravity. It is the background parameter against which all change is measured, and it never changes itself. It has a direction from past to future, but the equations of Newtonian mechanics are symmetric under time reversal. If you film a collision of billiard balls and play the film backward, the reversed film still shows a valid Newtonian trajectory. The laws do not distinguish past from future. The direction of time, the arrow that says this is the past and that is the future, must come from somewhere other than the fundamental equations. Einstein demolished the absolute character of time in 1905 with special relativity. Time, in special relativity, is not universal but relative. Different observers in different states of motion experience different rates of time passage. Two events that are simultaneous for one observer are not simultaneous for another moving relative to the first. There is no universal now, no cosmic tick of the clock that applies identically to all observers. Time and space are mixed into a four-dimensional spacetime continuum, and different observers slice that continuum into time and space in different ways, like different people cutting a loaf of bread at different angles. The mixing of time and space into spacetime is not merely mathematical. It has physical consequences that have been verified with extraordinary precision. Muons produced by cosmic ray collisions in the upper atmosphere survive long enough to reach the surface of the Earth despite having a half-life that, at rest, would cause them to decay well before reaching the ground. Their internal clocks run slower because they are moving at close to the speed of light relative to the ground frame, so they experience less time than we do, and therefore survive longer than we would naively expect. The time dilation is not an illusion. The muon genuinely experiences less elapsed time on its journey than the corresponding elapsed time measured by a clock at rest on the ground. General relativity deepens the revision. Not only does relative motion affect time, but so does gravity. Clocks run slower in stronger gravitational fields, a phenomenon called gravitational time dilation. This too has been verified precisely. Clocks on GPS satellites run faster than clocks on the Earth's surface because they are higher in the gravitational field and experience less gravitational time dilation, partially offset by the special relativistic time dilation from their orbital motion. The net correction must be applied to the satellite clocks, and it is not small. Without it, GPS positioning would accumulate errors of kilometers per day. The correction is applied because it works, because general relativistic time dilation is a real, measurable physical effect. In general relativity, time is not a background parameter, but a component of the dynamical spacetime geometry. The geometry of spacetime, including the rate of time flow at each point, is determined by the distribution of matter and energy through Einstein's field equations. Time is part of the solution to the equations, not part of the setup. This makes the concept of time's beginning much more subtle than it appears in classical physics. If time is part of the spacetime geometry, and the geometry is what begins at the Big Bang, then time itself begins at the Big Bang, or at whatever event corresponds to the earliest well-defined state of the geometry. This is not a new observation. It is implicit in general relativity and was emphasized by Stephen Hawking in his popular writings and in technical work with James Hartle. The point is that in a theory where time is part of the dynamical system, asking what happened before the beginning is asking about a time when there was no time. The question is not merely unanswered. It may be meaningless in the technical sense that the word before does not have a referent when there is no time for it to refer to. The arrow of time is a separate but related puzzle. The microscopic laws of physics, both classical and quantum, are essentially time-symmetric. They work the same way forward and backward in time, with the exception of a small violation of time-reversal symmetry in certain particle physics processes involving the weak interaction. This small violation is important but not large enough to account for the enormous asymmetry we observe in everyday life between past and future. The asymmetry we experience is macroscopic and overwhelming. Eggs break but do not spontaneously unbreak. Heat flows from hot to cold, not the reverse. Stars radiate energy outward and cool over time. Memories are of the past, not the future. None of these processes would look natural if filmed and played in reverse, and yet none of them is forbidden by the fundamental microscopic equations. They are statistical phenomena, arising from the overwhelming likelihood of transitions that increase entropy over those that decrease it. The second law of thermodynamics captures this statistically. In a closed system, entropy, a measure of the number of accessible microstates consistent with the macroscopic state, tends to increase over time. In a very large system with many degrees of freedom, the probability of entropy decreasing spontaneously is so small as to be effectively zero over any timescale we can observe. The time asymmetry of macroscopic phenomena is therefore a consequence of statistics applied to systems with many degrees of freedom, not a fundamental feature of the microscopic laws. But the statistical argument only explains why entropy tends to increase, not why it was low in the first place. To use the statistical argument, you have to assume a starting point with low entropy, and the statistical argument cannot explain that starting point without circularity. The arrow of time, as experienced in everyday life, ultimately points back to the low entropy of the early universe. The early universe was in an extraordinarily ordered low entropy state, and the macroscopic time asymmetry we experience is the consequence of that state plus the second law of thermodynamics. Why was the early universe in a low entropy state? This is the question Penrose has emphasized forcefully, and it does not have a settled answer. Any proposal for the beginning of the universe must grapple with this question, because the answer has implications for what the initial state was like and why it had the specific character it had. One set of answers appeals to the nature of the inflationary beginning. If inflation began in a smooth, nearly homogeneous state, then the post-inflationary universe inherits that smoothness and starts with low gravitational entropy, which is the relevant measure. As the universe expands and gravity amplifies small fluctuations into galaxies and black holes, gravitational entropy increases, driving the arrow of time. In this account, the low initial entropy is a consequence of the inflationary initial conditions, and the question shifts to why inflation began in a smooth state. Another set of answers, associated with the Hartle-Hawking no-boundary proposal, argues that the smooth, low-entropy beginning is a consequence of the no-boundary condition itself. In the no-boundary wave function, smooth geometries are exponentially favored over rough, chaotic ones. If this is correct, then the low initial entropy is not an additional assumption, but a prediction of the quantum cosmological initial condition. However, as we noted, the no-boundary proposal has been criticized for potentially favoring large fluctuations in some implementations, which would undermine this conclusion. Sean Carroll and others have approached the arrow of time from a different angle, arguing that the puzzle of low initial entropy is fundamental enough that it should be treated as a primary constraint on any theory of the beginning, not as a secondary consequence to be derived from some other principle. In Carroll's view, the low initial entropy is one of the most important observational facts about the universe, and a successful theory of the beginning must predict it. This sets a high bar for any proposal, and it is a bar that most current proposals struggle to clear convincingly. The deepest version of the arrow of time puzzle asks whether it is possible for time to have a direction at all in a universe where the fundamental laws are symmetric. If the laws do not distinguish past from future, why does the universe exhibit such a clear macroscopic distinction? The answer requires both the symmetric laws and the asymmetric initial condition. Without the low-entropy past, the symmetric laws would produce a universe in thermodynamic equilibrium with no arrow of time. It is the combination of time-symmetric laws and a specific initial condition that produces the observed time asymmetry. This means that the arrow of time is, in a deep sense, a cosmological phenomenon rather than a local one. It arises from the universe's history and initial state, not from any fundamental feature of the local physics. An observer in a different part of the universe, or in a universe with a different history, might experience a different or opposite arrow of time. The time direction we experience is the one that points away from the low-entropy past and toward the high-entropy future, and this direction is ultimately inherited from the initial conditions of the universe. The block universe interpretation of general relativity adds another layer to the picture of time. In general relativity, spacetime is a four-dimensional manifold, and all events, past, present, and future, exist as equally real points in this manifold. The distinction between past and future is not a feature of the spacetime itself, but of how we move through it, following time-like geodesics from lower time coordinates to higher ones. The present moment, the special now that we experience as the boundary between past and future, does not correspond to any special feature of the spacetime manifold. It is a feature of our experience, not of the fundamental geometry. This view is sometimes called eternalism or the block universe, because the entire spacetime history, from the Big Bang to the final state of the universe, is laid out as a complete, static four-dimensional block. Nothing in general relativity corresponds to the flow of time or the becoming of events. The physics describes the geometric structure of the block, and our subjective experience of moving through time from past to future is a consequence of our nature as thermodynamic systems with memories, not a feature of the fundamental physics. The block universe view is philosophically controversial and intuitively difficult to accept because it seems to conflict with our experience of time as flowing, as having a present moment that is different from both past and future. But the conflict may be resolved by noting that our experience is itself a physical process occurring within the block, and that the experience of a flow of time is what a thermodynamic system with a memory oriented toward the past would necessarily experience, given the arrow of time. The flow is real as experience, but not as fundamental physics. If the block universe view is correct, then the universe, in the full four-dimensional sense, does not come into existence at any point in time. It just is as a complete spacetime block. The beginning is not a creation event, but the earliest part of the block, the boundary of the spacetime manifold in the past direction. Asking what caused the Big Bang, in the context of the block universe, is asking what caused the boundary of the block to be where it is, and that question may not have a temporal answer because the block includes time within it. This does not mean the question has no answer. It may have an answer in terms of the laws of physics and the principles that determine the structure of the block, but the answer would be a structural or mathematical explanation rather than a causal one. It would say the block is this shape rather than that because the laws have these properties, not because something earlier made it so. This is a different kind of explanation from what we normally consider a causal explanation, and whether it is satisfying is partly a matter of what we require of explanations. The emergence of time in quantum gravity is the most technically challenging aspect of the origins problem, and it requires engaging with the mathematical structure of quantum gravity candidates. But the core idea can be explained at a level that captures its physical significance without getting lost in formalism. In canonical quantum gravity, which is the framework from which the Wheeler-DeWitt equation emerges, the quantum state of the universe is defined on the space of three-dimensional spatial geometries, called superspace. The Wheeler-DeWitt equation tells you which states in superspace are physically allowed, essentially encoding the constraint that the total energy of the universe, including gravitational energy, must be zero. This constraint, called the Hamiltonian constraint, is what makes quantum gravity timeless. It says that the quantum state does not evolve, because the generator of time evolution, the Hamiltonian, is constrained to be zero. A universe with a zero Hamiltonian has no time evolution in the usual sense. The wave function does not change. Everything is frozen. And yet we observe a universe in which things change, in which clocks tick, in which processes unfold sequentially. Where does this apparent time evolution come from if the fundamental description is timeless? The answer, in the approach called the conditional interpretation or the Page-Wooter's mechanism, is that time is relational. It is not that nothing changes in the timeless universe. It is that different parts of the quantum state are correlated with each other, and we can define an effective time coordinate by conditioning on the value of some particular degree of freedom. For example, if we define time as the reading of a particular clock, then the state of the rest of the universe conditional on the clock reading a certain value defines the quantum state at that effective time. As the clock reading changes, the conditional state of the rest of the universe changes, giving the appearance of time evolution even though the fundamental state is timeless. This relational time is operational. It is defined by correlations within the quantum state, not by any external background. It is real in the sense that it predicts the correlations we observe between physical systems. But it is emergent in the sense that it is derived from the timeless fundamental description, not fundamental itself. The emergence of time from the timeless Wheeler-DeWitt equation is not just a technical trick, it has physical implications. In particular, it implies that time is only well-defined when the quantum state has the right kind of entanglement structure, when there exist degrees of freedom that can serve as reliable clocks. In the Planck epoch, near the quantum gravitational beginning, this structure may not be present. The entanglement may be in a form that does not support a well-defined time variable, meaning that the concept of time may simply not apply in the very early universe, not because time was not present, but because the conditions for time to be defined were not yet met. This is a subtle but important point. Time does not emerge when the universe crosses some threshold of size or temperature. It emerges when the quantum state has the right structure to support relational correlations that can define a time coordinate. In the deep Planck regime, the quantum state may be in a superposition of different geometries and time structures, with no single dominant geometry, and therefore no single dominant time direction. The universe at its beginning in this picture is not in a specific time. It is in a superposition of all possible time structures, and the specific time we experience emerges as the quantum state decoheres into a near-classical geometry. Decoherence is the process by which quantum superpositions become effectively classical through interaction with an environment. In the early universe, there is no pre-existing environment external to the universe. But the universe can decohere internally, with different degrees of freedom playing the role of system and environment relative to each other. As the universe evolves from the Planck epoch into the inflationary epoch and beyond, the quantum state decoheres into an increasingly classical geometry, and the classical time coordinate emerges as part of that decoherence. The arrow of time and the classicality of the large-scale geometry are both consequences of this decoherence, not pre-existing features of the Planck epoch state. The concept of decoherence also helps us understand one of the most persistent puzzles in quantum cosmology, why the universe appears classical at large scales when the fundamental description is quantum mechanical. In ordinary quantum mechanics, systems become effectively classical when they interact with a large environment. The interaction entangles the system with the environment, spreading the quantum coherence across many degrees of freedom, and making it practically impossible to observe interference effects. The system then behaves as if it has definite classical properties, even though the fundamental description is still quantum. In quantum cosmology, the universe has no external environment, but the universe is large enough that different parts of it can serve as environments for each other. The large-scale geometry can become entangled with and effectively decohered by the many degrees of freedom of matter and radiation. The large-scale classical spacetime we observe is then not a fundamental feature of the universe, but an approximate description that emerges from the quantum state when most of the relevant degrees of freedom are traced over. This quantum-to-classical transition matters for the origin question because the Big Bang, as a beginning of classical spacetime, may not be a fundamental event but an emergent one. The transition from quantum gravitational regime to classical spacetime is not a sharp event happening at a specific time. It is a gradual process by which the quantum state becomes increasingly well described by a classical geometry. The beginning of classical time is not the beginning of the universe, but the beginning of the regime where classical descriptions are valid. Before classical time, in the quantum gravitational regime, there is still a quantum state. That state is timeless in the Wheeler-DeWitt sense, but it has structure. It has a wave function on superspace, and that wave function determines the probabilities for different classical spacetimes to emerge. The beginning of classical time is therefore a prediction of the quantum state rather than an ultimate origin. And the ultimate origin, if there is one, is whatever determined the quantum state in the first place. This regress is genuine and not easily closed. The quantum state on superspace is the most fundamental description available in canonical quantum gravity. What determines that state? The Hartle-Hawking and Vilenkin proposals are attempts to answer this question by specifying boundary conditions on the wave function. But boundary conditions are themselves something. not nothing, and the question of why those specific boundary conditions rather than others is not answered within the framework. Causality in the context of a universe with emergent time requires careful treatment. In ordinary physics, causality is the requirement that causes preceded effects in time. This requirement is built into the structure of relativistic field theory through the light cone. Effects cannot propagate faster than light, and the light cone structure ensures that causes in the past can influence events in the future but not vice versa. Causality is a fundamental organizing principle of the physical framework, but causality presupposes time. If time is emergent, then causality is also emergent. At the level of the timeless Wheeler-DeWitt equation, there is no causality in the ordinary sense. The wave function on superspace does not evolve, and there is no temporal sequence in which causes precede effects. What replaces causality at this level is a structural relationship between parts of the wave function, a timeless correlation that, when interpreted through the emergence of time, gives rise to effective causal relationships. This means that asking what caused the Big Bang may be asking for a causal relationship in a domain where causality has not yet emerged. The question is not merely unanswerable given our current knowledge. It may be malformed in a way that only becomes apparent when we take seriously the emergent nature of time. A better question might be, what structural features of the quantum gravitational wave function give rise to the emergent classical spacetime that looks like a hot Big Bang from the inside? This question can, in principle, be answered within the framework of quantum cosmology, even if the answer involves unfamiliar concepts. The philosophical tradition has long grappled with the question of whether causality requires time or whether there could be atemporal causal relationships. Some philosophers have argued that causality is more fundamental than time, and that causal structure is what gives rise to temporal ordering, not vice versa. In this view, the causal structure of the universe is primary, and time is derived from it. This is the view embodied in the causal set approach to quantum gravity, where the fundamental structure is a discrete set of events connected by causal relations, and the spacetime geometry is derived from this causal structure. Other philosophers have argued that causality requires time as a prerequisite, that without temporal ordering, there is no meaningful distinction between cause and effect. On this view, in a timeless fundamental description, there are no causes, only correlations, and the demand for a cause of the Big Bang is a category error, applying a concept that requires time to a domain where time does not exist fundamentally. Physics cannot definitively settle this philosophical debate, but it can inform it. The Wheeler-DeWitt equation and the candidate quantum gravity frameworks give us a concrete context in which the relationship between time and causality can be examined mathematically, and the mathematical examination suggests that both concepts are emergent rather than fundamental. This supports the view that asking for a cause of the Big Bang, in the deepest sense, is asking a question that presupposes more structure than the fundamental level of description possesses. The concept of nothing is similarly complicated when examined carefully, and its complications matter for what the beginning question is really asking. In everyday language, nothing means the absence of anything. No objects, no space, no time, no laws, no mathematics. This is sometimes called ontological nothingness or absolute nothingness, and it is extremely difficult to think about coherently, because even the statement nothing exists is itself a statement, invoking at least the concept of existence and the logical structure needed to make statements. Absolute nothingness may not be a coherent concept at all, at least not one that can be explored within any framework that has enough structure to support exploration. In physics, nothing has a more specific and less extreme meaning. The physical nothing is a vacuum, the lowest energy state of a physical system. The quantum vacuum is not empty in the classical sense. It has a specific energy density, zero-point fluctuations, and a rich structure determined by the fields that exist and their interactions. It is the background against which particles are defined as excitations. It is something, not nothing, though it is the minimal something within a given theoretical framework. The confusion between philosophical nothing and physical nothing has generated a great deal of unproductive debate, particularly in discussions of whether quantum mechanics can explain the universe's origin from nothing. When physicists say the universe can arise from a quantum vacuum fluctuation, they do not mean it arises from absolute nothingness. They mean it arises from a quantum state with minimal structure, a state that has a specific wave function, a specific set of fields, and a specific set of physical laws. This is not nothing in the philosophical sense, and conflating the two senses of nothing obscures what is actually being claimed. The distinction matters for the origin question because the philosophical question, why is there something rather than nothing, is asking about absolute nothingness. No physical answer can address this question, because any physical answer starts from some physical framework, which is not absolute nothingness. The scientific question, what are the initial conditions and the mechanism for the beginning of our observable universe, is asking about something much more specific and much more tractable. It is a question that physical theories can address in principle, even if they have not yet fully resolved it. Being clear about which question you are asking is essential for making progress. If you are asking the philosophical question, then you need to accept that no physical theory will answer it completely, and that the honest response is philosophical engagement with the limits of explanation. If you are asking the scientific question, then you can evaluate the candidate physical theories and the observational constraints and make progress in the normal scientific way. The most interesting and honest position is to acknowledge both questions, to understand what each requires, and to see how the scientific investigation changes the character of the philosophical question, even if it does not answer it. As physics pushes the beginning further back, explaining more through dynamical mechanisms and quantum principles, the philosophical question of ultimate existence becomes sharper and more isolated. What needs explaining becomes smaller, not in the sense of less significant, but in the sense of more precisely identified. Physics and philosophy narrow down together toward the core of what remains unexplained. The anthropic principle is one attempt to address the apparent fine-tuning of the universe for the existence of complex structures and observers. It comes in weak and strong forms, and the distinction matters enormously for its scientific status. The weak anthropic principle is an uncontroversial observational selection effect. We can only observe a universe that permits observers. Therefore, the fact that we observe a universe compatible with our existence is not surprising, regardless of whether most universes in some ensemble would be incompatible. This is a straightforward application of selection bias, and it is scientifically unobjectionable. It tells us that the observed properties of the universe are filtered by our presence, not that they are explained by our presence. The strong anthropic principle makes a much stronger claim, that the universe must have the properties required for observers to exist, or that observers play a fundamental role in determining the universe's properties. In its more extreme forms, this borders on mysticism or idealism and has little scientific content. But in the context of the landscape and eternal inflation, a more restrained form of the strong anthropic principle becomes relevant. If the multiverse contains regions with all possible combinations of physical constants and laws, then observers can only arise in regions where the constants and laws permit complex structures. The properties we observe are then a combination of what the landscape makes available and what the selection requirement of observers imposes. This conditional anthropic reasoning is scientifically meaningful if the multiverse is real, and if the distribution of physical constants across the landscape can be calculated. Then becomes a prediction, albeit a statistical one. The observed values of physical constants should be in the range that permits observers, and specifically should be typical among observer-containing regions rather than unusual. If we find ourselves in a highly atypical region of the observer-permitting range, that would be evidence against the anthropic framework, because the framework predicts we should be typical. The problem is that calculating typicality requires knowing the measure, the probability distribution over regions of the multiverse, and this is the measure problem we have already discussed. Without a well-defined measure, we cannot calculate what a typical observer-containing region looks like, and the anthropic prediction becomes vacuous. The measure problem is the central technical obstacle to making the anthropic approach scientifically predictive, and it is not solved. Despite this, anthropic reasoning has had some genuine predictive success, most notably in Weinberg's pre-1998 estimate of the cosmological constant. Weinberg argued that if the cosmological constant is drawn from a distribution of values across a multiverse, the observed value should be the largest value compatible with galaxy formation, because observers require galaxies. He estimated this maximum value and found it within 2 orders of magnitude of the subsequently observed value, which is a striking success given the many orders of magnitude range of possibilities. Whether this constitutes genuine scientific prediction or post hoc rationalization is debated, but the coincidence is at least suggestive. The cosmological constant is, in fact, the strongest argument for the anthropic landscape approach, because the discrepancy between the naive quantum field theory prediction and the observed value is so enormous that no non-anthropic explanation has succeeded. Either the cosmological constant is fine-tuned by some unknown mechanism that does not require a multiverse, or it is selected anthropically from a distribution of values across a multiverse, or there is some other explanation we have not yet conceived. The The first option has been sought intensively without success. The second requires the multiverse and a measure. The third is an admission that we are missing something fundamental. The cosmological constant problem is therefore both a challenge and a clue. It may be the most important quantitative hint we have about the structure of the underlying theory, pointing either toward supersymmetry or toward some other symmetry that enforces near-zero vacuum energy, or toward the existence of a vast landscape of vacua that anthropic selection explores. Which of these directions leads to the correct understanding will be determined by future developments in both theory and observation. The passage from classical to quantum descriptions of the universe is not merely a technical upgrade. It changes the meaning of physical reality in ways that bear directly on what the beginning of the universe means. In classical physics, the universe has a definite state at every moment. A point in phase space or a configuration of fields describes everything that is true about the universe at a given time. Evolution is deterministic. Given the state at one time and the laws, the state at all other times is uniquely determined. The universe has a definite history, a single trajectory through phase space or configuration space. In quantum mechanics, the universe does not have a definite state in the same sense. The quantum state is a wave function, a superposition of many possible configurations, each contributing with a complex amplitude. Measurement selects one outcome, but between measurements, the universe is in a superposition. Determinism holds at the level of the wave function, which evolves according to the Schrödinger equation, but the outcomes of specific measurements are probabilistic. In quantum cosmology, the universe as a whole is described by a wave function, and there are no external observers to make measurements. The wave function of the universe is not subject to collapse by an external measurement. It evolves according to the Wheeler-DeWitt equation, timeless and deterministic at the fundamental level. But interpreting this wave function as a description of observable reality requires additional structure, a way of extracting probabilities from the wave function, a way of defining what counts as an observation in a universe with no external observer, and a way of understanding the emergence of classicality from the quantum substrate. The many worlds interpretation of quantum mechanics is one approach to these questions. In this interpretation, the wave function always evolves unitarily without collapse, and what appears to be a measurement outcome is a branching of the wave function into multiple branches, each describing a different outcome with a different observer who experienced it. The universe in this interpretation is not a single classical history, but an enormous superposition of histories, all real in some sense, evolving together according to the Schrödinger equation. Applied to quantum cosmology, the many worlds interpretation suggests that the universe's wave function contains many branches, each corresponding to a different classical spacetime geometry and matter distribution. Our observable universe is one branch, the one that produced our local region with our specific history. Other branches contain other histories, other physics, other levels of complexity. The beginning of the universe in this picture is the beginning of the full wave function on superspace, not any specific classical history. The many worlds interpretation is mathematically clean and avoids the need for an external observer or a collapse mechanism, but it requires accepting that all the branches are real in some sense, which is a significant ontological commitment. It also requires solving the probability problem. In a universe where all outcomes occur, what does it mean to say that one outcome is more probable than another? The Born rule, which gives probabilities as the squared amplitudes of the wave function, must be derived or assumed rather than following trivially from the deterministic evolution. The decoherent histories approach, developed by Griffiths, Gell-Mann, and Hartle, is a related but more refined framework for quantum cosmology. It identifies a set of coarse-grained histories, sequences of approximate events that decohere from each other through the evolution of the quantum state. Decoherent histories can be assigned probabilities using the Born rule, and the set of decoherent histories corresponds to the approximately classical realm we experience. The framework is designed specifically for cosmological application, where there is no external observer, and it provides a systematic way of extracting classical descriptions from the quantum state. In the decoherent histories framework, the beginning of the universe is characterized by the wave function and its initial decoherent structure. Classical time and causality emerge gradually as the quantum state evolves and different degrees of freedom decohere from each other. The earliest moments, near the Planck epoch, are described by a quantum state with no well-defined decoherent histories, no classical geometry, and no well-defined time. The universe at this stage is genuinely quantum gravitational, without the classical scaffolding that the words beginning and time normally invoke. What does all of this imply for the question of what caused the Big Bang? The implications are multiple and they point in the same general direction. Causality, as ordinarily understood, requires time. Time, in the deepest physical frameworks we have, is emergent rather than fundamental. The Big Bang, as the beginning of classical time, is a feature of the emergent description rather than a fundamental event. Asking what caused the Big Bang in the ordinary causal sense is asking for a relationship that presupposes a temporal framework that did not yet exist at the level of the fundamental description. This does not mean the question has no answer. It means the answer, if it exists, will not have the form of a prior event causing the Big Bang. It will have a different form, a structural feature of the quantum gravitational state, a boundary condition on the wave function of the universe, a principle that selects among possible quantum states, or a mathematical necessity that makes the universe's existence a logical consequence of some deeper truth. None of these alternative forms of explanation is currently available in a complete, verified form. The proposals that exist, the no-boundary wave function, the tunneling wave function, the loop quantum cosmology bounce, are genuinely serious attempts to provide such an explanation, but they are incomplete and unverified. The territory between the available evidence and the complete explanation is genuine scientific and philosophical frontier, and occupying that frontier honestly requires holding both the strong evidence for what the universe has been doing and the honest uncertainty about why it began. One important thing that can be said is that the demand for a cause, in the most naive sense of an event that happened earlier and triggered the universe's beginning, is almost certainly asking the wrong question. The universe's beginning is not like the beginning of a fire or the beginning of a storm, events that have prior causes operating in the same temporal framework. The universe's beginning, whatever it actually was, occurred in a regime where the temporal framework itself was part of what was beginning. The ordinary concept of cause may not extend into this regime, and the question of the origin of the universe may need to be reformulated in a way that does not presuppose temporal causality. This reformulation is not a retreat from explanation. It is a recognition that explanation takes different forms at different levels of description, and that the deepest level of description may require a form of explanation that looks very different from what we are used to. Just as explaining the behavior of a gas in terms of statistical mechanics requires a different conceptual framework from explaining the behavior of individual molecules, explaining the origin of the universe may require a framework that operates by different principles than the causal narratives of everyday physics. The relationship between mathematics and physical reality is another dimension of the origin question that becomes impossible to avoid when we push to the deepest level. The physical proposals for the beginning of the universe all invoke mathematical structures: the Wheeler-DeWitt equation, the path integral over geometries, the wave function of the universe, the landscape of string theory vacua. These structures are not merely descriptive tools. In the quantum cosmological context, they are the fundamental description of reality, and the universe's existence is, in some sense, a consequence of their structure. This raises the question of why these mathematical structures rather than others, and why mathematical structures at all. Max Tegmark has argued provocatively that all mathematically consistent structures exist as physical realities, a view he calls the mathematical universe hypothesis. In this framework, our universe is one of many possible mathematical structures that exist, and the question of why our universe has the laws it has is answered by noting that we are the observers within the particular structure we inhabit. The deeper question of why mathematical structures exist at all is answered by saying that existence just is mathematical existence. To be real is to be a consistent mathematical structure. This is a striking and coherent philosophical position, but it is difficult to test scientifically. If all mathematical structures exist, then essentially everything is possible, and the selectivity that makes scientific predictions meaningful is hard to recover without additional principles that discriminate among mathematical structures. Tegmark argues that the measure over mathematical structures can be defined in terms of their descriptive complexity. Simpler structures are more probable, but implementing this measure is technically very difficult, and the resulting predictions are not specific enough to currently test. The more conventional view is that mathematical structures are descriptions of physical reality rather than constituents of it. In this view, the universe is not a mathematical object but a physical one, and mathematics is an extraordinarily effective language for describing it. Why mathematics should be so effective at describing physical reality is itself a puzzle, one that Eugene Wigner called the unreasonable effectiveness of mathematics in the natural sciences. The puzzle is genuine but perhaps has a mundane resolution. Mathematics is the science of structure, and physics finds mathematical structure in the world because the world has structure. The correspondence between mathematical and physical structure is then not miraculous but expected. Whatever one thinks of these philosophical options, the physical origin question connects to them through the quantum cosmological wave function. If the universe is described by a wave function on superspace, and if that wave function is determined by a principle like the no-boundary condition, then the universe's existence is in some sense a consequence of the mathematical structure of superspace, the Wheeler-DeWitt equation, and the boundary condition. Whether this means the universe was caused by its mathematical description, or whether the mathematical description is simply our best representation of an independently existing physical reality, is a question that physics alone cannot answer. What physics can do is identify which mathematical structures are required to describe the universe we observe and determine whether those structures predict or at least allow the beginning we find. This is the ongoing project of quantum cosmology, and it is a genuinely productive one, even if the deepest philosophical questions remain open. Let us turn to one more aspect of time that matters for the origin question, the possibility that time is not just emergent but fundamentally directional at the deepest level. We noted that the microscopic laws of physics are time-symmetric, with small exceptions. The arrow of time in macroscopic experience comes from the low-entropy initial condition, not from any fundamental time asymmetry. But what if there is a fundamental time asymmetry at the quantum gravitational level that has not yet been identified? Some researchers have proposed that quantum gravity introduces a fundamental arrow of time through the irreversibility of quantum gravitational processes near singularities, or through the specific nature of the quantum boundary conditions at the Planck epoch. Roger Penrose's conformal cyclic cosmology introduces a specific time asymmetry through the second law of thermodynamics applied across multiple eons of cosmological evolution. In this picture, the universe undergoes a conformal rescaling at the endpoint of one eon to the beginning of the next, and information about the gravitational entropy of the previous eon is encoded in the CMB anomalies of the next. This is a concrete, testable proposal, and some claim detections of concentric rings in the CMB have been associated with it, though the statistical significance of those claimed detections is disputed. Lee Smolin has proposed that natural selection operates among universes, with black holes spawning new universes with slightly modified physical constants, and universes that produce more black holes producing more offspring. This cosmological natural selection would select for universes with parameters that maximize black hole production, and Smolin has argued that the observed values of physical constants are consistent with this optimization. The proposal introduces a time asymmetry through the reproductive process, with later universes being modifications of earlier ones, and it provides a mechanism for the fine-tuning of constants through evolutionary dynamics rather than anthropic selection. These are speculative proposals, and their scientific status depends on whether they make testable predictions that can be confirmed or refuted with current or future observations. Penrose's conformal cyclic cosmology makes specific predictions about patterns in the CMB that can be searched for with existing data. Smolin's cosmological natural selection makes predictions about the relationship between physical constants and black hole production that can be explored by varying the constants in theoretical models. Whether either proposal is ultimately correct, the important thing is that they illustrate the variety of approaches that have been taken to the time asymmetry and origin questions, and the range of physical intuitions that have informed serious scientific thinking about these issues. What have we established in this part about time, causality, and what they mean for the question of cosmic origins? We have established that time, even in the well-tested framework of general relativity, is not an absolute background, but a dynamical component of spacetime geometry that can vary locally and that begins, in some sense, with the universe itself. We have established that the arrow of time, the experienced direction from past to future, is a macroscopic, emergent phenomenon rooted in the low entropy of the early universe, rather than in any fundamental time asymmetry in the microscopic laws. We have established that in quantum gravity, time appears to be emergent from a more fundamental, timeless description, arising through relational correlations within the quantum state rather than being given from outside. We have established that causality, as ordinarily understood, presupposes time and is therefore also emergent in the quantum gravitational context. Asking what caused the Big Bang may be asking for a temporal causal relationship in a domain where time and causality are not yet defined. The question, while natural, may be formulated in the wrong conceptual language for the domain it is asking about. We have established that nothing in the physical sense is very different from nothing in the philosophical sense, and conflating the two leads to confusion about what physical theories of the beginning actually claim. The physical proposals for the origin of the universe invoke mathematical and physical structures that are not absolute nothingness, and they should be evaluated on their merits as physical theories rather than as answers to the philosophical question of why there is something rather than nothing in the ultimate sense. We have established that the block universe interpretation of general relativity, the many worlds interpretation of quantum mechanics, and the decoherent histories approach to quantum cosmology all provide frameworks in which the universe's beginning can be discussed without presupposing that something external to the universe caused it. In each of these frameworks, the beginning is a feature of the structure of the universe's quantum state or spacetime geometry, not the result of an external causal action. And we have established that the most productive reformulation of the origin question, given everything physics has learned, is not what caused the Big Bang, but rather what structural feature or principle of the deepest physical description gives rise to a classical spacetime that looks, from the inside, like it began with a hot, dense Big Bang. This question can be addressed scientifically, makes contact with observational constraints, and connects to the ongoing research programs of quantum cosmology, quantum gravity, and observational cosmology. The question is hard. The answer is not yet known. But the question, properly formulated, is a scientific question in the deepest sense, not merely a philosophical one, and the tools for approaching it are being developed with increasing sophistication. The universe does not yield its deepest secrets easily, but it does yield them, slowly and precisely, to patient and disciplined inquiry. In the final part of this investigation, we will bring together all of the threads we have been following, from the observational evidence for the hot Big Bang through the inflationary mechanism, the bouncing cosmologies, the quantum cosmological proposals, and the nature of time and causality, and we will ask what the most honest and most complete account of the universe's origin looks like given everything we know. We will examine what observational programs over the next decade and beyond are most likely to provide new constraints on the origin question. We will look at the prospects for a theory of quantum gravity that can extend our description into the Planck epoch. We will consider what kinds of explanations remain possible and what kinds are effectively ruled out by what we already know. And we will sit with the deepest remaining uncertainty, the question of why there is a physical universe at all rather than nothing, with the honesty that such a question deserves. The investigation is not over. It may never be over in the sense of reaching a final, complete answer to every form of the origin question. But the investigation has made enormous progress, and the progress is real, cumulative, and increasingly precise. That is not nothing. That is, in fact, everything that science can offer, and it is more than enough to justify the inquiry. Every investigation reaches a point where the territory ahead becomes less charted than the territory behind, where the neat progression of established results gives way to a landscape of competing hypotheses and open questions. We have arrived at that point. Behind us lies some of the most successful and precisely tested science in human history, a framework for the universe's evolution that spans 13.8 billion years and is anchored to multiple independent lines of evidence, each confirming the others with remarkable consistency. Ahead lies the Planck epoch, the quantum gravitational regime, and the ultimate question of why anything exists at all. The contrast between the confidence of what is behind and the uncertainty of what is ahead is itself one of the most important things this investigation has revealed. It would be easy, and it would be wrong, to treat that uncertainty as a failure. The universe does not owe us clean answers. It does not organize itself around what would be satisfying to explain. What the uncertainty actually represents is the precise localization of where our current understanding ends, and that precision is itself a form of knowledge. We know with considerable confidence that our current physical framework works back to fractions of a second after the hot dense phase began. We know that it fails in a specific and identifiable way at the Planck scale. We know which properties of the early universe are measured and which are explained and which are merely assumed. We know which observations are most likely to provide new constraints on the nature of the beginning. Knowing where the map ends is different from knowing nothing about the territory. This final part takes stock. It assembles everything that has been established across the investigation and presents it in the most honest form available, neither inflating confidence beyond what the evidence supports nor deflating it through excessive caution. It then looks forward at the observational programs and theoretical developments most likely to transform the picture, and it ends by confronting the deepest questions that may never fully yield to scientific investigation, asking what the right relationship between those questions and the scientific inquiry actually is. The most important thing to establish clearly at the outset of this synthesis is what the hot Big Bang model actually says and does not say, stripped of the accretions of popular misunderstanding that have accumulated around it. The hot Big Bang model says the observable universe evolved from an early state of extreme temperature and density, that this state was spatially uniform to high precision and expanding rapidly, that as it expanded it cooled through a sequence of well-understood transitions producing first quarks and gluons, then protons and neutrons, then light nuclei, then neutral atoms, then the first stars and galaxies, and eventually the structured cosmos we inhabit today. It says that the radiation left over from the early thermal phase fills all of space today as the cosmic microwave background, that the light elements were synthesized in the first minutes in proportions that can be predicted and observed, and that the large-scale distribution of galaxies reflects the amplified residue of tiny primordial density fluctuations. All of this is well established by multiple independent measurements. The hot Big Bang model does not say there was an explosion. It does not say the universe expanded into pre-existing empty space from a central point. It does not say the universe was created. It does not say anything about what, if anything, preceded the hot dense phase. It does not claim to describe the first instant of time. The singularity that appears when the equations are extrapolated backward is a mathematical feature of the model, not a physical description of a real state. It marks where the model breaks down, not where the universe began in some ultimate sense. These distinctions are not pedantic. They determine what the model can and cannot support as explanations. The model supports the conclusion that the universe has been evolving for billions of years in ways that are now well understood. It does not support the conclusion that the universe began from nothing, or that it was created by an external cause, or that the Big Bang was a literal explosion, or that the singularity was the first moment of time. All of these claims require additional assumptions or interpretations that go beyond what the model itself asserts. The inflationary model extends the hot Big Bang account by proposing an earlier period of accelerated expansion that set the initial conditions for the hot phase. It explains several features of the observed universe that the hot Big Bang alone leaves unexplained: the uniformity, the flatness, the absence of relics like magnetic monopoles, and the near-scale invariant spectrum of primordial density fluctuations. The inflationary model has received genuine empirical support from the CMB measurements, particularly from the measurements of the spectral index NS, its departure from exact scale invariance, and the consistency of the primordial fluctuations with Gaussian statistics. The inflationary model does not explain what drove inflation. It invokes an inflaton field whose identity is unknown and whose potential is constrained by observations but not derived from any fundamental theory. It does not explain the inflaton's initial conditions. It does not explain what happened before inflation. It replaces one boundary condition with another, moving the edge of the map without eliminating the map's edge. This is genuine progress, because the new boundary is less fine-tuned in some respects than the old one, but it is not a complete explanation. Quantum cosmological proposals attempt to describe the Planck epoch and the nature of the beginning using the tools of quantum mechanics applied to spacetime geometry. The Hartle-Hawking no-boundary proposal and the Vilenkin tunneling wave function are the most developed of these, and they make predictions about the initial state of the universe that differ from what a purely classical model would imply. They attempt to eliminate the need for an initial condition imposed from outside by deriving the initial state from a quantum principle, a boundary condition on the wave function of the universe. These proposals are mathematically sophisticated and conceptually significant, but they remain incomplete, and their physical interpretation is contested. Bouncing cosmologies attempt to replace the singularity with a physical transition from a prior state, embedding the hot Big Bang in a larger temporal context. Loop quantum cosmology implements this through discrete quantum geometry. Ekpyrotic and cyclic models implement it through brane dynamics in higher dimensional spaces. These proposals also make specific predictions that differ from inflation in particular ways, especially regarding the primordial gravitational wave spectrum. None of them is as well developed or as well connected to verified physics as the inflationary framework. The multiverse, arising from eternal inflation in the context of the string theory landscape, provides a possible context in which the conditions for our universe arise naturally and repeatedly. But it introduces severe difficulties for scientific prediction through the measure problem, and it raises philosophical questions about the nature of scientific explanation when an infinite ensemble of unobservable universes is invoked. The multiverse is a serious scientific proposal, but it is not established, and its implications for the origin question are deeply uncertain. This is the landscape of current understanding, and it is genuinely vast and genuinely incomplete simultaneously. The evidence is strong for what the universe has been doing. The theory is well developed for how it evolved. The physics is speculative, but serious for what generated the initial conditions. And the deepest questions about why it began at all remain open in a way that may never be fully closed. One of the most important lessons of the investigation is about the relationship between precision and understanding. We can measure the properties of the early universe with extraordinary precision. The CMB power spectrum is measured to better than 1% accuracy over a wide range of angular scales. The primordial helium abundance is known to a few percent. The baryon density is constrained to a fraction of a percent. The spectral index of primordial fluctuations is measured to 3 significant figures. These are not approximate descriptions. They are detailed numerical specifications of the universe's early state, and yet this precision does not translate directly into understanding of the origin. We know precisely what the universe was doing at 380,000 years and at a few minutes. We know the parameters that describe it at those epochs to impressive accuracy, but precision about the state does not tell us why the state was what it was. It tells us that if you specify certain initial conditions and physical laws, the universe evolves into something that matches what we observe. It does not tell us why those initial conditions rather than others, or why those physical laws rather than others, or why anything at all. This gap between precision and understanding is not unique to cosmology. It appears throughout science whenever a theory successfully describes a system without explaining why the system exists or why it has the specific character it has. We can describe the hydrogen spectrum with extraordinary precision using quantum mechanics, without explaining why quantum mechanics is the correct description of atomic physics. We can describe evolution with great detail and predictive power without explaining why chemistry gives rise to self-replicating molecules in the first place. Precision about the how does not automatically give understanding of the why, and this gap is especially acute when the why involves the existence of the entire system rather than the behavior of some part of it. The appropriate response to this gap is not to fill it with unfounded speculation, and it is not to dismiss the questions the gap raises as unscientific. The appropriate response is to be clear about what has been explained and what has not, to work systematically toward better explanations using both theoretical and observational tools, and to be honest about the limits of what can be explained within any physical framework. This is the scientific attitude, and it applies to the origin question just as much as to any other question in physics. The observational frontier for the coming decade offers several opportunities to significantly constrain the origin question, and these opportunities deserve careful attention because they represent the places where the investigation will make its next major steps. The search for primordial gravitational waves through CMB B-mode polarization remains the single most important observational test of inflationary cosmology. The current upper limit on the tensor-to-scalar ratio R is approximately 0.36, already ruling out the simplest large-field inflation models. The next generation of ground-based CMB experiments, particularly the Simons Observatory currently operating in Chile and the future CMB S4 project, will push this limit to below 0.3 or better. At this sensitivity level, a significant fraction of the remaining inflationary model space will either be detected or eliminated. A detection of primordial B-modes at the level of R greater than roughly 0.1 would be transformative. It would confirm that inflation occurred at an energy scale well above the electroweak scale, somewhere near the grand unification scale. It would pin down the inflationary energy to within an order of magnitude, connecting inflation to particle physics in a direct way. It would also confirm that quantum gravitational effects, specifically quantum fluctuations of the spacetime metric, are observable in the CMB. This would be the first observational window into quantum gravity, however indirect, and it would represent an extraordinary scientific achievement. A non-detection of primordial B-modes at the CMB S4 sensitivity level would be almost equally informative, though more constraining than confirming. It would eliminate all natural large-field inflation models, pushing viable models into a regime of small-field dynamics with plateau-like potentials. This would pose challenges for theories of the inflaton's identity, since most particle physics-motivated candidates for the inflaton tend to predict large-field behavior. The absence of a gravitational wave signal would also be consistent with bouncing cosmologies like the ekpyrotic scenario, though it would not by itself confirm any specific alternative to inflation. The challenge of measuring primordial B-modes requires controlling two major foreground contaminations. The first is polarized thermal emission from dust in our own galaxy, which has a frequency dependence different from the CMB signal and can in principle be subtracted using multifrequency observations. The second is the gravitational lensing of E-mode polarization into B modes by the intervening mass distribution. This lensing B-mode signal has already been measured and characterized, and its subtraction, known as delensing, can be improved by using external mass maps from galaxy surveys or CMB lensing measurements. Both foreground separation and delensing are active research areas, and improvements in both will be necessary to reach the sensitivity targets of next-generation experiments. The measurement of the primordial gravitational wave spectrum's frequency dependence would be even more informative than a single amplitude measurement, because different inflationary models predict different spectral shapes for the tensor power spectrum. Inflation in general predicts a slight red tilt, with more power at lower frequencies, while alternatives like the ekpyrotic scenario predict a steep blue tilt. Measuring the spectral shape would therefore directly discriminate between these classes of models. This requires not just CMB measurements, but also direct gravitational wave detection at lower frequencies through space-based interferometers like LISA, which is sensitive to gravitational waves at millihertz frequencies, and pulsar timing arrays, which are sensitive at nanohertz frequencies. The combination of CMB measurements and gravitational wave direct detection across many decades of frequency would provide an extraordinarily powerful probe of the early universe. A stochastic gravitational wave background with a specific spectral shape, detected consistently across multiple observational methods, would be strong evidence for the mechanism that produced it. Conversely, the absence of such a background at various frequency ranges would constrain the energy scale and duration of any early universe processes that could have produced gravitational waves. The measurement of non-Gaussianity in the primordial perturbation spectrum is another important observational target. Single-field slow-roll inflation predicts very small non-Gaussianity, characterized by the parameter FNL being of order the slow-roll parameters, typically less than 0.1 in magnitude. Current limits from Planck on local-type non-Gaussianity are FNL equals 0.9 plus or minus 5.1, consistent with 0 and with the small values predicted by single-field inflation. But the precision is not yet sufficient to test the slow-roll prediction directly. Future surveys, particularly spectroscopic galaxy surveys like the Euclid mission and the Dark Energy Spectroscopic Instrument, will measure the large-scale structure of the universe with sufficient precision to constrain FNL at the level of 1 or better. Reaching FNL of order 1 would begin to probe the regime where single-field inflation's predictions differ from multi-field models and other alternatives. A detection of non-Gaussianity at the level of FNL equal to several would be a clear indication of physics beyond single-field slow-roll inflation, pointing toward multiple fields or non-trivial dynamics during inflation. The detection of primordial gravitational waves and the measurement of non-Gaussianity together would provide powerful complementary constraints. They probe different aspects of the inflationary dynamics. The tensor amplitude reflects the energy scale and field range, while non-Gaussianity reflects the interactions and additional fields present during inflation. The joint constraints from these two probes would dramatically narrow the space of viable inflationary models and could point toward a specific physical identification of the inflaton. Scale-dependent non-Gaussianity, where FNL varies with the scale of the fluctuation, is another signature that can distinguish between single-field and multi-field inflation models. Some multi-field models predict a specific scale dependence that could be detected in galaxy surveys as a scale-dependent bias in galaxy clustering. This effect is subtle but distinctive, and its measurement would provide information about the number of fields and their interactions during inflation that is not accessible from the power spectrum alone. The 21-centimeter line of neutral hydrogen, as mentioned in the previous part, offers a window into the cosmic dark ages between recombination and reionization, a period from roughly 380,000 years to about 1 billion years after the hot dense phase. During this period, the universe was filled with neutral hydrogen that has not yet been ionized by the first stars. The hyperfine transition of hydrogen produces a spectral line at 21 centimeters in the rest frame, which is redshifted to meter wavelength radio frequencies for emission from the high redshift universe. Mapping the three-dimensional distribution of this emission would probe the matter-power spectrum on small scales, the formation of the first stars and galaxies, and potentially signatures of exotic early universe physics. The challenge of 21-centimeter cosmology is foreground contamination. Radio frequency interference from terrestrial sources and from bright astrophysical foregrounds, particularly synchrotron emission from our galaxy and from radio galaxies, is many orders of magnitude brighter than the 21-centimeter signal. Separating the cosmological signal from these foregrounds requires exploiting the spectral smoothness of the foregrounds compared to the rapidly varying cosmological signal. This is technically demanding, and progress has been slow, but experiments like Hera, Meerkat, and ultimately the Square Kilometre Array are making steady improvements in sensitivity and foreground control. A successful measurement of the 21-centimeter power spectrum across the cosmic dark ages and reionization epoch would provide constraints on the primordial power spectrum complementary to and extending those from the CMB, probing scales smaller than those accessible to CMB experiments. It would also constrain the thermal and ionization history of the intergalactic medium, providing information about the first sources of ultraviolet radiation and X-rays in the early universe. Any anomalies in the 21-centimeter signal, departures from the predictions of the standard model of reionization, could indicate new physics from the early universe, whether exotic dark matter decay, primordial magnetic fields, or other early universe relics. Direct detection experiments for dark matter, while not directly constraining the inflationary model, are crucial for understanding the nature of the universe's ingredients, and therefore for understanding what the universe was like in its earliest moments. Dark matter constitutes roughly 27% of the universe's energy budget and plays a crucial role in structure formation. Its identity is unknown, but its properties are constrained by multiple observations to be cold, meaning its thermal velocity was small when structure formation began, non-baryonic, meaning it is not made of protons and neutrons, and only weakly interacting with ordinary matter. The leading candidates for dark matter have been weakly interacting massive particles, or WIMPs, with masses in the range of tens to hundreds of GeV. These candidates have been searched for extensively in underground detectors, at the Large Hadron Collider, and through indirect detection of their annihilation products in space. Despite very sensitive searches, no confirmed detection has been made, and the parameter space for WIMP dark matter has been severely reduced. This is not conclusive evidence against WIMPs, but it has expanded interest in alternative candidates. Axions, originally proposed to solve a different problem in particle physics, the strong CP problem, have received increasing attention as dark matter candidates. They are much lighter than WIMPs, with masses in the range of microelectron volts to millielectron volts, and they interact with photons through a two-photon coupling. Experiments like ADMX use microwave cavities in strong magnetic fields to search for the resonant conversion of dark matter axions into microwave photons. Other experiments explore different mass ranges and detection techniques. The axion parameter space is large, and covering it comprehensively requires a diverse experimental program that is currently underway. Primordial black holes formed in the early universe represent another dark matter candidate that does not require new particle physics beyond the standard model. If density fluctuations in the early universe were sufficiently large on small scales, they could have collapsed directly into black holes before any stars formed. These primordial black holes would be stable on cosmological timescales if they are massive enough, and they could constitute some or all of the dark matter. The parameter space of possible primordial black hole mass and abundance is constrained by multiple observations, including microlensing surveys, the CMB, and gravitational wave observations. Current constraints leave open some mass windows, particularly around the asteroid mass range, where primordial black holes could still be significant components of dark matter. Gravitational wave observations are particularly interesting for primordial black holes because a population of primordial black holes would produce mergers detectable by LIGO, Virgo, and KAGRA, as well as a stochastic background from early universe primordial black hole formation. The mass distribution of observed black hole mergers is one of the constraints on the primordial black hole scenario, and future improvements in sensitivity will either detect or further constrain the primordial black hole contribution. Identifying dark matter would transform our understanding of the early universe. The dark matter particle's properties, its mass, its interaction cross-section, its production mechanism, would tell us about physics at whatever energy scale it was produced. If dark matter is a WIMP produced by thermal freezeout at the electroweak scale, that provides information about the electroweak era. If it is an axion produced by the misalignment mechanism, that provides information about the QCD era and about possible symmetry breaking events at much higher energies. Dark matter identification would be a major step toward understanding the universe's complete inventory and the processes that produced it. The nature of dark energy remains one of the deepest mysteries in physics, and its understanding is directly connected to the origin question through the cosmological constant problem. If dark energy is the cosmological constant, its value is so extraordinarily small compared to theoretical expectations that either a profound mechanism of cancellation exists that we do not understand, or the value is selected anthropically from a landscape of possible values, or we are missing something fundamental about the relationship between quantum field theory and gravity. New surveys of the large-scale structure and expansion history of the universe, particularly from the Euclid satellite and the Vera Rubin Observatory's legacy survey of space and time, will measure the dark energy equation of state with unprecedented precision across a wide range of cosmic history. If the equation of state differs from -1, the value for a pure cosmological constant, or if it varies with time, that would indicate that dark energy is a dynamical field rather than a fixed vacuum energy. Such a detection would transform our understanding of dark energy and provide crucial input for theories of the vacuum structure and its connection to the beginning. The combination of weak gravitational lensing, galaxy clustering, and supernova distances from these surveys will constrain the dark energy equation of state parameter W and its time derivative to a few percent or better. Distinguishing between W equal to -1 and W differing from -1 by even a few percent requires controlling systematic errors at a level that is technically challenging but achievable with the planned instruments. Any significant deviation from W equal to -1 would be a major discovery, comparable in importance to the original discovery of cosmic acceleration in 1998. Understanding dark energy better would also constrain the stability of our vacuum. If dark energy is a quintessence field slowly rolling toward a potential minimum, the vacuum we inhabit might be metastable, with a certain probability of decaying to a lower energy state. The decay would proceed through bubble nucleation, with the bubble expanding at the speed of light and converting the physics within it to the lower energy vacuum. Understanding whether our vacuum is stable or metastable, and if metastable, what its lifetime is a question of both practical and philosophical importance. Practical because a metastable vacuum could decay at any time, philosophical because it connects to the larger question of whether our universe is a long-lived accident or a stable outcome. The measurement of the Higgs boson's mass at 125 GeV, combined with the measured top quark mass, places the standard model vacuum in a region that is metastable rather than absolutely stable. The lifetime of the metastable vacuum is much longer than the current age of the universe, so the vacuum is stable on cosmological timescales, but the metastability raises the question of whether some process in the early universe, perhaps associated with inflation or reheating, might have stabilized the vacuum or driven a transition to a more stable state. These questions connect particle physics, cosmology, and the origin question in ways that future measurements of the Higgs and top quark properties will continue to probe. Theoretical developments in quantum gravity are harder to predict on decadal timescales than observational developments because they depend on mathematical insight that does not follow a regular schedule. But several directions are actively pursued and show promise for transforming the understanding of the Planck epoch. The holographic principle and the ADS-CFT correspondence have provided powerful tools for understanding quantum gravity in specific settings. ADS-CFT is a precise mathematical equivalence between a theory of gravity in anti-de Sitter space, a negatively curved spacetime, and a non-gravitational quantum field theory on its boundary. This duality allows gravitational problems to be mapped to non-gravitational ones, sometimes making the gravity problem more tractable. Applications to cosmological settings are challenging because our universe is de Sitter-like at late times, not anti-de Sitter, but progress is being made in extending the holographic framework to more cosmologically relevant geometries. The idea that spacetime is an emergent phenomenon arising from quantum entanglement has gained significant traction through work connecting quantum information theory to quantum gravity. The Ryu-Takayanagi formula, which relates the entanglement entropy of a region in the boundary field theory to the area of a minimal surface in the bulk gravity theory, suggests that the geometry of spacetime is in some deep sense encoded in the entanglement structure of the quantum state. Work by Mark van Romstonk and others has made this connection more explicit, showing that geometric connectivity, the fact that different regions of space are connected rather than separate, corresponds to entanglement between the quantum degrees of freedom describing those regions. If spacetime geometry is emergent from entanglement, this has profound implications for the beginning of the universe. At the Planck epoch, or before the emergence of classical spacetime, the quantum state would be in a form where the entanglement structure does not yet support the connectivity we associate with a smooth, classical spacetime. The beginning of classical spacetime would correspond to the formation of a specific entanglement structure from a more disordered quantum state. This is a genuinely new way of thinking about the origin of spacetime, and it is being actively explored in the context of quantum information theory and quantum gravity. Loop quantum cosmology has continued to develop as a framework for addressing the singularity. Recent work has extended the framework to include anisotropic cosmologies and models with matter fields more realistic than simple scalar fields, testing whether the bounce that replaces the singularity in simple models survives in more realistic settings. The extension to inhomogeneous cosmologies, which is necessary for a full treatment of perturbations through the bounce, is technically demanding but has made progress. The connection between loop quantum cosmology and the full theory of loop quantum gravity is still being established, and this connection is important for assessing whether the cosmological bounce is a genuine prediction of the fundamental theory or an artifact of the symmetry-reduced cosmological approximation. String theory and M-theory continue to be explored as frameworks for quantum gravity, with particular attention to the landscape and its implications for inflation and the cosmological constant. The Swampland program, which studies which effective field theories can arise from consistent string theory compactifications and which cannot, has produced a set of conjectured constraints on low-energy physics that have implications for inflation. The de Sitter conjecture, one of the Swampland conjectures, proposes that stable de Sitter space cannot arise in string theory, which would have dramatic implications for both inflation and dark energy. Whether the conjecture is correct remains contested, but the Swampland program has generated productive dialogue between string theory and observational cosmology. The information paradox for black holes, the question of what happens to information that falls into a black hole, has received renewed attention in recent years through the work of Pennington, Almery, Mahajan, Maldacena, and Zhao, and others on the island formula and the entropy of Hawking radiation. This work suggests that black hole evaporation is unitary, meaning information is preserved, and that the entanglement structure of the quantum state plays a crucial role in how information escapes. The implications for cosmology are still being worked out, but the techniques developed in this context, involving replica wormholes and gravitational path integrals, may be applicable to quantum cosmological questions about the beginning. The philosophical dimensions of the origin question that physics cannot fully resolve deserve honest and careful treatment, because they are genuine questions rather than pseudo-questions, and because the relationship between the scientific and philosophical aspects of the origin question matters for how we understand what the science is actually telling us. The question of why there is something rather than nothing, in the strict philosophical sense of absolute nothingness, is not answerable by any physical theory. This is not because physics is limited, but because any physical answer presupposes a physical framework, which is itself something rather than nothing. The regress of explanation cannot be terminated by any physical principle without presupposing that principle, which leaves the existence of the principle unexplained. This is not a defect of physics, it is a structural feature of explanation itself. Every explanatory system, physical, mathematical, or otherwise, has presuppositions that are not themselves explained within the system. This does not mean the question is meaningless. It means the question reaches a level where the standard tools of scientific explanation run out and philosophical analysis takes over. Leibniz asked the question in the 17th century, why is there something rather than nothing? And the question remains open in the same fundamental way it was then, despite all the progress physics has made. Physics has enormously enriched the context in which the question is asked. It has made precise what something means in the physical context, what the laws are that govern it, what the history of that something has been, but it has not answered why there is anything to be described by those laws. The philosopher and physicist can engage productively on this question if they are clear about what each discipline contributes. Physics contributes precision. It tells us what kind of something we have, what its properties are, what its history has been, and what constraints any account of its origin must satisfy. Philosophy contributes conceptual analysis. It clarifies what kinds of questions can be asked, what would count as an answer, and how the limits of explanation should be understood. Neither is sufficient alone, and the combination is more illuminating than either separately. The question of why the physical laws are what they are is closely related and only partially more tractable than the question of why there is something rather than nothing. Physics can describe the laws and test their predictions, but it cannot, within any single framework, explain why those laws rather than others. A deeper theory can explain the laws of a shallower theory, in the sense of deriving the shallower laws from more fundamental principles, but the deeper theory has its own laws that are not explained within it. The chain of explanation always terminates somewhere, at a set of fundamental principles that are simply taken as given. This regress may terminate in mathematical necessity, if there exists a mathematical structure that is the only consistent possibility, and that happens to be realized physically. This is what the string theory landscape approach gestures toward, in the sense that string theory is argued to be a highly constrained framework with limited freedom. But the landscape's enormous number of possible vacua argues against the uniqueness of the solution, and the question of why string theory itself, rather than some other mathematical framework, is not answered within string theory. Mathematical necessity, as a termination of the regress of explanation, requires identifying a unique, necessary mathematical structure, which has not been done. An alternative termination of the regress is a brute fact. The universe simply exists with these laws, and no deeper explanation is available or needed. This is philosophically defensible, in the sense that every explanatory chain must start somewhere, and there is no logical necessity that every fact have an explanation external to itself. But it may not be satisfying to those who feel that the existence and specific character of the universe demands explanation, and it does not connect to any physical framework in a productive way. A third option is the multiverse and the anthropic principle, in which the universe has the laws it has, because those are the laws in the pocket of the multiverse that we happen to inhabit, and we inhabit it because it is among the pockets compatible with observers. This converts the question of why these laws into a question of probability distribution over the multiverse and anthropic weighting, which may in principle be scientifically tractable, but faces the measure problem that makes definite predictions elusive. None of these options is clearly correct or clearly satisfying, and the honest assessment is that we do not know how the chain of explanation terminates, if it terminates at all. This is not a temporary ignorance that will be resolved by the next generation of experiments or the next theoretical breakthrough. It is a deep structural feature of the enterprise of explanation applied to the universe as a whole. The most honest thing that can be said is that the question is genuine, the current answers are incomplete, and the investigation is ongoing. What can be said with confidence, drawing together everything established in this investigation, is that the universe has a detailed, measurable history that extends back to fractions of a second after the hot, dense beginning, and that this history is described by a framework of extraordinary predictive success. The universe began in a state of extreme temperature, density, and uniformity, expanded and cooled through a sequence of well-understood transitions, and assembled into the complex structures we inhabit today from tiny primordial fluctuations in density. This account is not speculation. It is one of the most thoroughly tested scientific achievements in human history. The account does not fully explain itself. The initial conditions that made it possible, the smoothness, the flatness, the specific spectrum of primordial fluctuations, are not derived from first principles within the hot Big Bang model. The inflationary model provides a dynamical explanation for these initial conditions and is supported by observations of the CMB, but it relies on an inflated field whose identity and potential are not fully explained and on initial conditions for inflation that are themselves not fully understood. The Planck epoch, where quantum gravitational effects become essential, is described by frameworks that are either incomplete or untested or both. The question of what caused the Big Bang, examined carefully, turns out not to be a simple causal question with a straightforward answer. It involves the nature of time, which turns out to be emergent in the quantum gravitational context rather than fundamental. It involves the nature of causality, which presupposes time and is therefore also emergent. It involves the meaning of nothing, which in the physical context is not absolute nothingness, but a quantum state with specific properties. And it involves the limits of explanation itself, the structural fact that every explanatory framework has presuppositions that it cannot itself explain. The most honest answer to the question of what caused the Big Bang is therefore layered. At the level of tested physics, we can say the universe evolved from an early hot dense state, and inflationary dynamics may have set the conditions for that state. At the level of quantum cosmology, we can say the beginning of classical spacetime may have arisen from a quantum gravitational state through a transition that replaced the classical singularity. At the level of fundamental physics, we do not yet have a verified theory of quantum gravity that can fully describe the Planck epoch, and the nature of the transition from quantum to classical remains unclear. At the philosophical level, the question of ultimate causation, of why anything exists at all, remains open in a way that may be structural rather than contingent. The investigation of cosmic origins matters beyond its scientific content, and it matters in ways that connect to the deepest human concerns. We are the only species we know of that asks where the universe came from. We are the only part of the universe, as far as we can tell, that can examine the universe's own history and attempt to understand its beginning. This capacity for self-reflection and cosmic investigation is itself one of the most remarkable features of the universe, arising from the same processes, the same physical laws, the same cosmic history that the investigation is trying to understand. There is something philosophically vertiginous about this. The universe has evolved over 13.8 billion years in such a way as to produce entities that can investigate the nature of the universe's beginning. Investigation looks back through time, using instruments and mathematical tools developed over centuries of intellectual effort, and it finds that the universe has been telling its own story in the form of light, chemistry, and structure, waiting for someone with the tools to read it. This is not an argument for any particular metaphysical conclusion. It is an observation about the relationship between the investigator and the investigated that gives the investigation an unusual character. In most areas of science, the scientist and the object of study are clearly separated. The physicist studying a particle is not the particle. The astronomer studying a star is not the star. But the cosmologist studying the origin of the universe is part of the universe, made of the same atoms, governed by the same physical laws, evolved through the same cosmic history. The investigation is, in some sense, the universe investigating itself. This reflexive character of cosmological investigation does not change the physics. The CMB temperature is what it is regardless of who is measuring it. The baryon-to-photon ratio is what it is regardless of the philosophical position of the person calculating it, but it does change the significance of the investigation. The universe is not merely a backdrop against which human history unfolds. It is the context in which inquiry itself became possible, the system that generated the capacity to ask about its own beginning. The awe that many people feel when confronting the scale and age of the universe, the strange beauty of a CMB map, the intellectual vertigo of the Planck epoch, is not sentiment unrelated to science. It is a response to the genuine strangeness of the situation, and it is an appropriate response. The universe is genuinely strange. Its origin is genuinely mysterious. The investigation into that mystery is among the most demanding and most rewarding intellectual activities that human beings have undertaken, and the fact that we can undertake it at all is itself one of the universe's most remarkable properties. The discipline that this investigation requires is worth stating explicitly, because it is easy to drift from what is established to what is merely fascinating, and the drift matters. The discipline consists of several habits of mind that the investigation of origins demands more acutely than most areas of science. The first habit is distinguishing measurement from inference, and inference from speculation, and being explicit about which is which at every stage. Measurements are direct observational results with quantified uncertainties. Inferences are conclusions drawn from measurements using theoretical frameworks that may themselves be uncertain. Speculations are proposals that go beyond what current data can constrain, guided by theoretical considerations but not yet tested. Mixing these categories without labeling them creates a false impression of confidence and muddies the waters of what the investigation has actually established. The second habit is keeping track of assumptions. Every calculation and every theoretical framework rests on assumptions, and those assumptions may or may not be valid in the regime being discussed. In early universe cosmology, we frequently assume that the standard model of particle physics applies at energies above those where it has been tested, that general relativity is the correct description of gravity at scales we cannot directly probe, and that quantum mechanics extends to systems as large as the universe. These assumptions may be correct, but they are assumptions rather than verified facts, and the conclusions drawn from them have the same tentative status as the assumptions. The third habit is taking seriously the possibility that the question is malformed. This is an unusual habit in science, because most scientific questions have the right structure, and the task is to find the answer rather than to question the question. But at the boundaries of space, time, and causality, where the conceptual framework of the question may not apply, the most important scientific move may be to reformulate the question in a way that can actually be addressed. Asking what caused the Big Bang may be asking for a temporal causal relationship in a domain where time and causality are not applicable, and recognizing this may be more valuable than generating elaborate answers to the wrong question. The fourth habit is holding open questions open without filling them with preferred answers. This is emotionally difficult because open questions are uncomfortable, and the temptation to settle them with a compelling story is strong. The story about inflation, for example, is compelling and has genuine empirical support, but it is not complete, and treating it as complete as the final explanation for the universe's initial conditions, would close off investigation of what lies beyond it. The open questions should be kept explicitly open, identified as open, and pursued with the rigor that their genuine openness demands. The fifth habit is recognizing that the investigation has intrinsic value independent of whether it reaches a complete answer. The investigation of cosmic origins is not worth pursuing only if it eventually explains everything. It is worth pursuing because each step of understanding, each constraint on the beginning, each measurement that narrows the space of possibilities, is genuine knowledge that adds to the sum of what humanity understands about the universe and its own place in it. The journey matters even if the destination is unreachable. There are questions in the investigation that deserve special status because they are simultaneously scientifically tractable and philosophically profound, combining the precision of physics with the depth of philosophy in ways that neither discipline alone can match. One such question is whether the laws of physics are the same throughout the universe and across all of cosmic history. We assume they are, and this assumption underlies the entire investigative framework. But the assumption is not trivially correct. In a multiverse where different regions can have different low-energy physics, the laws we observe locally may be different from those in other regions. Eternal inflation populates different vacuum states with different effective laws, and our pocket may not be typical even among observer-containing pockets. Testing whether the laws are truly universal requires looking for variations in physical constants across cosmic time and space through spectroscopic measurements of distant quasars and absorption systems. Current measurements show no significant variation, but the sensitivity is limited, and the question remains worth asking. Another profound question is whether the universe has a purpose or direction in some scientific sense, not in the teleological sense of being designed for a goal, but in the sense of having a preferred direction of evolution that reflects some deeper feature of the laws. The second law of thermodynamics gives time a direction, from low entropy to high entropy, and this direction is cosmological in origin, rooted in the initial conditions of the universe. But is there any sense in which the evolution of complexity, from simple plasma to atoms to molecules to cells to minds, reflects more than just the statistical tendency of entropy to increase? Some researchers have argued that complexity increases over cosmic time in a way that cannot be explained purely by entropy increase, pointing to something like a cosmological drive toward complexity. Others argue that complexity is just a way station between simple low-entropy states and final high-entropy equilibrium, with no deeper significance. This question matters for the origin question, because if the universe has a tendency toward complexity, that tendency might be reflected in the initial conditions or the laws in a way that could be detected. A universe fine-tuned for complexity is different from a universe fine-tuned purely for observer existence, and the distinction might in principle be observable. But the question is difficult to make precise, and it is important not to import teleological assumptions under scientific language. The question of consciousness and its relationship to the physical universe is sometimes raised in the context of the origin question, particularly through the lens of the observer-dependent interpretations of quantum mechanics. In the Copenhagen interpretation, wave function collapse requires an observer, and in some formulations, observer and observed are not fully separable. If this creates a role for consciousness in the fundamental description of physical reality, it could change the relationship between the origin of the universe and the existence of observers. The participatory universe idea, associated with John Wheeler, suggests that observers play a role in bringing reality into definite existence through their observations. These ideas are controversial and are not part of mainstream physics, but they illustrate the range of positions that serious physicists have taken on the relationship between the observer and the observed universe. Whether consciousness plays any role in the fundamental description of reality is deeply uncertain, and the mainstream view is that it does not, that physics describes an observer-independent reality, and the appearance of observer dependence in quantum mechanics can be explained without invoking consciousness. But the question is live enough to deserve honest acknowledgement rather than dismissal. The arc of the investigation, from the CMB and element abundances through inflation and quantum cosmology to the nature of time and the limits of explanation, has a shape that is worth reflecting on before we conclude. The arc begins with measurement with precision, with the hardest and most reliable evidence available. It proceeds through increasingly theoretical and increasingly uncertain territory, tracking how far solid ground extends and where the footing becomes less sure. It ends not with a definitive answer, but with a precise identification of the open questions and the tools most likely to make progress on them. This shape is the shape of science at its best at the frontier. It does not pretend to know what it does not know. It does not dress speculation in the language of established fact. It does not close off questions prematurely with plausible-sounding answers that have not been tested. And it does not despair at what remains unknown, but treats the unknown as a target, a place where the next generation of instruments and ideas will venture. The universe has been telling its story for 13.8 billion years in the form of light, chemistry, gravity, and structure. We have been listening carefully for a few centuries and paying close attention for a few decades. What we have heard is extraordinary. A universe with a precise age, a measurable composition, a traceable history, and a beginning that looks increasingly specific and increasingly constrained, even as it remains incompletely understood. The story is not over. In some sense, it has barely begun. The instruments being built now will hear parts of the story that no previous generation could detect. The theoretical frameworks being developed now will translate those observations into understanding that no previous framework could provide. The questions being formulated now, about the quantum nature of the Planck epoch, about the emergence of time, about the meaning of nothing at the boundary of physical description, are the right questions for the next generation to pursue. And the question that drives all of it, the question that human beings have asked in every culture and every era, the question that sits at the center of every cosmological investigation and every philosophical tradition that has ever taken the universe seriously, remains as powerful and as open as it ever was. Where did all of this come from? Why is there anything at all? What was there before the beginning? We have better tools to investigate those questions than any previous generation. We have better constraints on the space of possible answers. We have better frameworks for understanding what kinds of answers are scientifically meaningful and what kinds of answers require philosophical rather than physical engagement. We have honest acknowledgement of where the investigation stands, what has been established, what remains open, and what may never be fully resolved. That is not a small thing. That is the work of centuries of accumulated inquiry, carried forward by generations of scientists who looked at the sky and refused to be satisfied with easy answers. The universe does not give up its deepest secrets without a fight. But it does give them up slowly and precisely to those with the patience and the rigor to listen. The investigation continues. The questions are alive. The universe is still speaking. And the most important habit we can cultivate, as individuals and as a species, is the willingness to listen without knowing in advance what we are going to hear.